Today we're going to do another math marathon. Specifically, we're going to do 100 integrals today. So in the description below, I'll put a link to the file for this specific worksheet and some videos that are similar to this one that I have inspired off of. So without further ado, let's get into it. The first question is going to be proving the fundamental theorem of calculus. So basically, that just means that the integral is just the antiderivative or the reverse derivative. For some of us, it is just a fact of life that the integral and the antiderivative, they're just the same thing. But for those that are really looking for the facts, you might be asking why. Why is the integral the antiderivative? Well, here is the proof. So the integral is basically just an analog for the area under a function, a curve or function. So it's like a sum, but for a continuous range or under a function. Let me show you what I mean. So for example, we got a curve here, and we want to find the area between 0 and this, let's say x. So that's going to be, this is the integral or the area under the curve. So from there, we need to find some kind of formula to interpret the area, because this isn't a good shape. So a rectangle, its area is just length times width. A circle, its area is pi r squared, and so on, so on, so on, so on. But this is not a good shape. It's irregular. So how are we going to do this? Well, let's define some few functions first. So this is the curve y equals f of x. So the outputs here is just f of x. So for example, this is x. This point is f of x. So this point is x, then f of x. All right. So that is going to be what this point is. So f of x is like the y value. So mm, let's erase that for a moment. So let's define a of x as the area of this region. So a of x is defined as the area under f of x from 0 to x. So let's agree on that one, that a of x is the area from here all the way to here, whatever x it may be. So x may be 2, so it's the area from 0 to 2 under f of x. It should be above the x-axis as well. So let's define another point here. This point should be x plus h, and then here. So the area from here to x plus h is going to be a of x plus h is area from 0 to x plus h. So that's going to be that. So what we're trying to find is the area of this small bit here. The small bit here, the region from x to x plus h. We're trying to find the area of that little bit, that sliver, the tiny bar. Oh, a portion of the total area. So what is this? Well, we know that the area from a of x plus h, if we subtract a of x from that, we get this bar, because this is from here to 0, this is a of x, and then from here to 0 is a of x plus h. So if we just remove this, and then we get the area of just the bar. So this is equal to a of x plus h minus a of x. Minus a of x. But it looks like a rectangle, right? And h let's say h goes to 0. So this becomes smaller and smaller. H goes to 0. This becomes smaller and smaller. So the shape most closely resembles a rectangle. So we can approximate the area of this bar to be a rectangle. So the area of a rectangle is width times length. So the width is going to be h, and then the height is going to be, let's put it on the other side. The height is going to be f of x. So the area is going to be h f of x. All right. And let's equate these two together. So we get a of x plus h minus a of x equals h f of x. Let's divide both sides by h. All right. Where h here and here cancel each other out and they get deleted. All right. Next phase. And then we remember that h goes to 0. So we're going to take the limit as h goes to 0 of both sides. The limit as h goes to 0 of f of x is just f of x. And then this is just the definition of the derivative. You may be familiar with it if you've taken calculus 1. So this is going to be a prime of x, which is the derivative of a of x. And that's the proof. How is this a proof? Well, we've proved that the area function, which is basically what uh, uh, the integral is basically the antiderivative of f of x. If you look at here, the derivative of a is f. So going backwards, the antiderivative of f is a. So that's going to be the logic that we're going to be using for throughout this worksheet. So strap in, everyone. Question number 2. The integral of a times x to the n dx. So what is this? What is the integral of a times x to the n? So what we're going to do is actually the antiderivative of this. The derivative. So let's put something here. So y and then dy over dx. So let's have a chart here showing the derivative and the original function. So the original function is x to the n. So the derivative of that is n times x to the n minus 1. Now, our new derivative is x to the n. So what should be the antiderivative of that so that the derivative is x to the n? Well, we can see here that the power actually goes down by 1. So we really need the power to be n plus 1 here. So if we subtract 1 from there, it goes x to the n on the other side. But we do have to pay attention to the n plus 1 because it will be brought down. So we have to divide the original function by n plus 1 so that when we bring this down, it cancels. So n plus 1 here and then over n plus 1. This and that cancel each other out. So we get just x to the n. What's going to be the answer? The a is just a constant. The dx is the width of the bar. Remember earlier that we were representing this with h. Well, normally this could be also be represented with dx. So that's also a thing. So dx is the width of this thing. A is just a constant, so we can bring that outside. Much like the product rule, not the product rule, the coefficient rule or the constant multiple rule of derivatives. With integrals, the constant multiples, we can bring that outside. So this is equal to a times the integral of x to the n dx. So x to the n, we already found the integral that is just x times n plus 1 over n plus 1. And then we multiplied it by a, and then that's the answer. Or that's just one answer, and then we have to find all the answers. We need to add plus c. This is just the constant of integration. Remember, if you have a constant here, for example, let's have like 3, the derivative of that constant is going to be 0. So we need to be careful to add the c so we can include everything with a constant. So, for example, c could be 5, c could be pi, c could be 7, or whatever number you want, because its derivative is to 0. So it doesn't affect the final answer, just that uh, every we're including everything that is the derivative of this if we have c. So there we go. Just don't forget the c. Number three. Now, number three, the integral of e to the bx dx. So we know the derivative of e to the x is just e to the x. So no surprising, the antiderivative of e to the x is just e to the x. So this is going to be easy, but there's also b here, so we have to keep track of that. Because the derivative of e to the bx is, well, e to the bx, and then we have to multiply by uh, the derivative of the inside function, bx, which is b. So we need to divide this by b, so this can be divided by b. This does not cancel each other out to get the final answer, which is e to the bx. So this is going to be our integral over b. Then we add plus c, so just so we can we can include everything else. So that's the answer. 4 and 5 I'm going to include here because they're very similar. Sine of uh, ax, the integral from sine of ax dx, and also cosine ax dx. So what we can do here is to, well, we should know the derivatives of both sine x and cosine x because they're important. Derivative of sine x is cosine x. Derivative of cosine x is negative sine x. So if we have cosine here, we should have sine on the original, on the integral. Then we divide by a, since the chain rule will bring a to the front. So if we find the derivative of this, it goes cosine uh, ax times a all over a. The a's cancel out, so it will result into cosine ax being the original function, so we get that. And then, of course, plus c. For sine x is probably pretty much the same thing. So so this is positive, but this is negative. So we just add negative. We just multiply negative to cosine ax also over a. So we can get rid of the chain rule thing, the chain rule leftovers, and then we have the c. That's the answer. Question number 6. The integral of 1 over x squared dx. So 1 over x squared can also be described as expressed as negative x to the negative 2 dx. So this can be we can use the formula for x to the n. Remember the formula for x to the n earlier. This is x to the n plus 1 over n plus 1. So this is going to be x to the negative 2 plus 1 over negative 2 plus 1, which is going to be x to the negative 1 over negative 1 or negative 1 over x plus c. All right, don't forget plus c. That's going to be the answer. Question number 7. The integral of 1 over x dx. So this is just going to be x to the negative 1. So the integral is, of course, x to the negative 1 plus 1 over negative 1 plus 1 equals to, this is going to be x to the 0. So just 1 over negative 1 plus 1 is 0, which is not the answer. That is not the answer. This is wrong. This is all wrong. You know why? Because it results in 1 over 0, which is not good. So remember your derivatives. The derivative of ln x specifically is 1 over x. And this is 1 over x. So we're going to be uh, we're going to be going in reverse, so this has to be ln x and not 1 over 0 or whatever it was doing earlier. And then we just add plus c. So that's the antiderivative or the integral. Question number 8. And question number 9. I'm going to include that. Sinh of x dx and cosh x dx. For the sinh one, well, I mean, uh, we need, let's remember the derivatives of sinh and cosh. The derivative of sinh is just cosh of x, and the derivative of cosh is just sinh of x. So this is going to be easy. There's no sign differences here. So this is just going to be cosh. Let's see. It's going to be sinh plus c. Don't get it confused, even though it's like the integral is not the derivative. It's just that their derivatives are the same with each, but it just cycles basically. Question. Oh, question number 10. The derivative of 1 over 1 plus x squared dx. For this one, you just have to remember your derivatives. Remember that arctan, its derivative is 1 over 1 plus x squared. So this is going to be arctan x plus c. And if you know your derivatives, you can very well know your integrals for that. So there you go. Question number 11. So for this part, we're going to do integration by substitution. So what is integration by substitution? I will show you what it is. So the integral of 2x over 1 plus x squared. Earlier, we had 1 over 1 plus x squared, arctan and all that. But what about 2x over 1 plus x squared? What can we do here? Well, we can use a substitution technique. So look at this. Let this bottom here, if I substitute that into u, we can abandon that, But we need the sacrifice or we need to adjust it to the u world. So for example, the derivative of this is 2x times dx. Derivative of u is just 1 times du. Now 2x dx equals du. This is 2x dx. So we should replace that with u. Du over 1 plus x squared is now u, so just u. This is, by the way, this is just 1 over u du. 1 over u, derivative of that is just ln of u. Or ln of 1 plus x squared. There. But since this is the 1 plus x squared is always positive, we can just ignore the absolute values. And then we add plus c. And that's going to be the derivative, the integral, sorry, of our function. There you go. So that's how you do integration by substitution. So the next one is the integral of tangent x. So we all know that tangent x is equals to sine x over cosine x. So let us substitute cosine x as u. U is the favorite letter of mathematicians when it comes to this kind of thing. So let's just roll with u. So we need to find the derivative of this. Negative sine x dx is equals to du. Why are we finding the derivative? Because we need to find dx somewhere in there. So that's why we're finding the derivative. So negative sine x is here, but the negative is nowhere to be seen. So we just multiply negative to both sides. So sine x dx equals negative du. So we get derivative of negative du over the no integral over cosine x. Uh, no, not cosine x. Sorry. U. This is negative ln of u, which is negative uh, ln of cosine x. This can be law of. We can use the law of logarithms here. So we can get ln of 1 over cosine or ln of secant x plus c. That's going to be the integral of tangent. 13. Uh, Integral of ln x over x dx. So let ln x be u. The derivative of ln x is 1 over x. Then we multiply by dx. And then du right here. So this is 1 over x. Basically, this is ln x times 1 over x dx. This will become du. This will become u. And we're finding the integral of that. So u du, which is u to the power 1, basically. So this is going to be u to 1 plus 1 over 1 plus 1, which is u squared over 2, which is going to be ln x, then parentheses squared, not ln x squared, but ln x parentheses squared over 2 plus c, because we don't forget the c, and that is the answer. Question number 14. The integral of e to the arctan of x over 1 plus x squared dx. One trick to find the what to substitute it is to find the derivative of somewhere else. So arctan x is something that is very difficult to 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 include in our calculations, but we know that 1 over 1 plus x squared exists here. I mean, there's 1 over 1 plus x squared on the bottom right here. So what we can do instead is to uh, substitute arctan x to be u, and then the derivative of arctan x is just 1 over 1 plus x squared dx is the u. Separate this, we get e to the arctan x multiplied by 1 over 1 plus x squared dx. This becomes du. This becomes u. So eu du. That's a bit far. So let's just put it somewhere near. Eu du. So the integral of e to the u is just e to the u. Or e to the arctan x, you have to revert it back to x world. And then plus c. That's the integral. Question number 15, sorry. Question number 15. Secant x dx. That's the integral of secant x. Well, now for here, we have to kind of multiply both numerator and denominator by something else, because normally this is like impossible to do this straightforward without any substitution. So let's see. What we do first is to multiply both this and the denominator by secant x plus tangent x. And for the sake of clarity later, let's revert this tan x plus secant x. Remember, this and that is just equal because it's just a commutative property, so nothing problematic here. And we get secant squared x plus secant x tangent x over tangent x plus secant x. Can you see it? Let us substitute tan x plus secant x as u. Secant tangent x derivative is secant squared x. Oh, forget the x here. And then secant x is secant x tangent x. All of that times dx is equals to du. See it now? This and dx is du. And this is going to be 1 over u. This is now ln of u, which is ln of secant x. Let's just maintain it. Tangent x plus secant x plus c. That's going to be the derivative integral of secant x. So good. Question 16. The integral of e to the x plus 2 over e to the x plus 2x plus 1 dx. So here, the derivative e to the x is e to the x, derivative of 2x is 2. Let's put the entire thing on the bottom here as the derivative. Again, if there's a constant in here, it's not a problem because the derivative constant is 0. So let's put e to the x plus 2x plus 1. Sorry. Let that be equal to u. So e to the x plus 2 uh, parentheses dx is equals to du. Would you look at that? Look at that. Look at that. That is going to be du over u, which is going to be this. So this will be ln of u. The absolute value is there, so it is not negative, which is now we turn it back to x. So ln of e to the x plus 2x plus 1. Let's see. That's the answer. Question number 17. Uh, x cubed over 2 plus x squared. Now for this one, there's an x cubed in here instead of an x or a 2x, but we don't have to worry about that. Let's just turn this into the x here. Something I think is much easier. Times over 2 plus x squared. It's just x squared here, but we have to put the x somewhere, and we have to put it here. All right. So for this case, we have to let x squared be u, and 2x dx is going to be du. All right. But we only have x dx, so we have to divide both sides by 2. So we get x dx equals 1 half du. So let's replace everything with what we have. So this is u over 1 plus u multiplied by 1 half the u. So this u and 1 plus u, we can add 1 here. So we get u plus 1 over u plus 1, which is just 1. We have to subtract 1 though. So we get that. 1 half we can bring to the outside since it is just a constant. Then the integral of u plus 1 over u plus 1, we can flip that back. Minus 1 over u plus 1 times du. Okay? So this is going to be 1. This is going to be 1 over u plus 1. So 1 half times the integral of 1 is u. Because the derivative of u is 1. So that's going to be u minus 1 half then ln of u plus 1. That is fine because the derivative of 1 is just 0. So it doesn't affect the chain rule whatsoever. And then we substitute it back to the x world. So this is going to be 1 over 2 x squared, sorry, minus 1 half ln of x squared plus 1 plus c. That is the answer. Oh, no, 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 wrong, wrong. Wait, wait, wait. This should be 2. Oops, sorry. This should be 2. This should be 2. So this is 2, and this is 2. So this is going to be 1 half ln, so this is nothing. Then u plus 2, so x squared plus 2, and then the 1 half here does it. So that's the correct answer. I misjudged it on the first time, but that's the answer. So if you turn that into derivative, you'll get uh, the answer. And I think that's correct. Let me just check. Literally. That is. That's not here. Well, anywho, let's try other stuff. Let's try number 80. I think that's correct. I didn't write it the first time. Anyway, number 18. X squared e to the x cubed dx. Now, x cubed, we can substitute as u. And then 3x squared dx is equals to du. Now, we have x squared and dx here. X squared dx. The 3 we can divide by 3. So, x squared dx is 1/3 du. So, that's going to be the substitution. So 1/3 du here, e to the u here. So this is going to be 1/3. Then the integral of e to the u is just e to the u, no, not u, equals to 1 over 3 e to the x cubed plus c. And that is the answer. 19. The integral of cosine ln x over x dx. Again, we can just put ln x as the substitution. So just put the derivative of both sides. 1 over x dx is equals to du. 1 over x, we have that one here, and dx is this. So we just transform it into du. Then cosine of ln x is now just u. So cosine u, the integral of that is as going to be sine of u, or sine of ln x plus c. Now, question number 20. It's going to be difficult. X plus 2 multiplied by x squared plus 4x plus 3 to the power of 10 dx. So what is this going to be? Ooh. Well, we have to recognize what is the derivative of this? The derivative of this is 2x plus 4, or 2 times x plus 2. Hey, we have x plus 2 here. So why not substitute x squared plus 4x plus 3 to be u? Because the derivative is just 2 times x plus 2 dx du. We can just divide both sides by 2 to get x plus 2 dx is equals to du over 2. So we get integral of uh, du over 2. Then this is going to be u to the power of 10. So this is just u to the 11 over 11. Then we multiply that by 1/2. And then u to the 11 over 22 is, after multiplying 2 times 11, this is now going to be x squared plus 4x plus 3 to the power of 11 over 22 plus c. And that is the answer. Okay, for this next part is the integration by parts. And normally it would be a long journey to find the answer. But for this one, we're going to use the DI method. We're just finding the derivative and then the integral here. I recommend finding the actual reasons why the DI method, or what this method is actually doing. You can search tabular method, DI method, table method, whatever. I recommend you find the reasons to why it's doing so. We're going to be using that for the majority of these questions. 21. The integral of x squared e to the x dx. So for the d, what we want is something that eventually goes to 0, or is easier to derive than the others, or whatever. So let's put x squared here, because if we derive that, that would be 2x. Differentiate it again, we get 2. Differentiate again, we get 0. And if it goes to 0, this is, sorry, this is where we stop. Okay. Don't forget the plus minus here. Then we just integrate the rest, e to the x, and then e to the x, e to the x, e to the x. All right. And then we multiply the diagonals like this. And we get the answer is x squared e to the x minus 2x e to the x plus 2 e to the x plus c. That's the entire answer. It's much easier than the other methods, but again, please know how this is actually done. Yeah, the long version, because that really helps with the understanding. 22. X times ln x dx. The Do we know the integral for ln x? No, not really. So we put the derivative uh, as ln x. And then the integral is x. You say, well, x goes to zero, right? But hear me out. We're going to be doing this miracle. So the derivative of ln x is going to be 1 over x. Derivative integral of x is x squared over 2. So we get x squared over 2 ln x. And one of the stops here is if we can evaluate this thing, because this is, we can integrate this. Minus integral 1 over x times x squared over 2, right? So, so can we evaluate this? Yes. This is, let's rewrite x squared over 2 ln x. Minus, we can cancel x and x here. We get x over 2, essentially, dx. We get x squared over 2 ln x minus the derivative of this is x squared over 4. X squared over 2 times 1 half x squared over 4. Then we have plus c, all right? So the second stop here is if the row is easily integrable. Okay. Next, question number 23. E to the x sine x 2x dx. So we just have the di here. Okay. For this one, e to the x sine 2x, none of them really go to zero or has a good derivative. So we just put somewhere here. So let's put sine 2x here and let's put e to the x here. Don't forget the plus minus plus here. The signs. So sine 2x, its derivative is 2 cosine 2x. Integral of e to the x is e to the x. And then the derivative of this is negative 4 sine 2x. Integral is e to the 2x. Observe, this thing is going to be negative 4 e to the 2x sine 2x. This is the original function. Then this is just a constant multiple. So what we're going to do is to do everything, do the diagonals. So this is going to be e to the 2x sine 2x minus 2e to the x, no, not 2x, so sorry. What did I do? No, no, not even. There. E to the x sine x, 2 to e to the x, cosine 2x minus 4 times the integral of e to the x sine 2x dx. What we're going to be doing, let me just erase this thing. What we're going to do is to add 4 integral of e to the x sine 2x dx to both sides. What is this going to do? Well, for starters, this is going to be 5 times integral e to the x sine 2x dx. And then on the right side, we get e to the x sine 2x minus 2 e to the x cosine 2x. And then the minus 4 and the plus 4, they cancel each other out. So we're left with this. So what we're going to do here is to divide it by 5. So we divide this by 5, this cancels out. We multiply both sides here by 5, 1 over 5. And there we go. And that's the integral. So for the third kind of stopping in the derivative, if you can spot a duplicate, for example, the e to the x sine 2x, or a multiple of the duplicate, you can stop right there. We can do this algebra thing, and then we can divide both sides by whatever the constant is, as long as you can find the duplicate, of course. Next. Uh, Integral of ln x over x cubed dx. Earlier it was ln x over x, now it's ln x over x cubed. So let's do the thing we did earlier. So ln x equals u, then 1 over x dx equals du. This time there are spare x's in here, so what we're going to do with it? Well, if we raise e to both sides here, we get x, since this and that cancel, equals e to the u. So we can separate this as ln x times 1 over x times 1 over x squared dx. This and that will become du. This will become u. And this, e to the x squared, this will become e to the negative u, 2u. Yeah, because this is going to 1 over e u then squared, which is 1 over e 2u, which if we take the numerator will be e to the negative 2u. We use the DI method, the integration by parts here. U can be in the derivative because that will go to 0. And then e to the negative 2u. The integral of e to the negative 2u is going to be negative 1 over 2 e to the negative 2u. And then integral of that is going to be negative 1 over 4. Oh no, positive 1 over 4 e to the negative 2u. We just multiply it diagonally. We get plus u times negative. So negative u over 2 e to the negative 2u minus 1 over 4 e to the negative 2u. And u, we go back, is just ln x. So uh, earlier, e to negative u is equals to 1 over x squared. So this is going to be 1 over x squared. And u is just ln x. So ln x over 2, the negative, minus 1 4 times 1 over x squared. Rearrange that, we get ln x, a negative ln x over 2x squared minus 1 over 4x squared plus c. That's the answer. It's much more complicated than the derivative, isn't it? That just comes with the job. Integral for number 25, integral of e to the 4x sine e to the 2x. Before we do anything rash here, let's do substitution first. So e to the 4x is just going to be e to the 2x and then squared. Then e to the 2 sine e to the 2x. X is here. So we can say e to the 2x, let's substitute that with u. So derivative of e to the 2x is going to be 2 e to the 2x is equals to du, dx here. Divide both sides by 2 in order to get e to the 2x dx is equals to du over 2. One of these we can sacrifice with dx. So e to the 2x is going to be du over 2. Then e to the, because this is e to the 2x times e to the 2x. This and that became du. E to the 2x will become u. And then the e to the 2x there inside sine will also become u. And then we have to find the integral of that. Rearrange a bit. 1/2 the integral of u sine of u du. This step we have to do integration by parts again. So open the du method. So u, derivative 1, then 0. So sine u here. The integral of that is negative cosine u, and then a negative sine of u. Then we just do the diagonals here, so we get negative u cosine u plus sine u. Uh, uh, Going back to the x world, we get negative e to the 2x cosine of e to the 2x plus sine of e to the 2x. And that's the answer. 26. X to the 4 cosine x. This is nothing special. This is basically just a longer version of integration by parts. So let's do it. Let's have plus minus. Yeah. So the derivative x to the 4. The integral, we can put cosine x here. So x to the 4, what's the derivative of that? 4x cubed. Derivative is 12x squared, and then again 24x, again 24, and then the last is 0. So we stop there. We cosine the integral is sine. The integral of that is negative cosine x, then negative sine x. It's just a cycle. So the next one is cosine x, and then sine x. It's a cycle, cycle of 4. So we just multiply all of these together to get our final answer. This is going to be very long, so hold tight. X to the 4 sine x minus minus becomes plus 4x cubed cosine x plus minus becomes minus 12x squared sine of x minus plus becomes minus 24x cosine x plus plus becomes 24 sine x plus c, and that is going to be the answer. It's long, you know. That's how it is. Imagine doing this with a longer method. I won't do it, even if you ask me to. 27. Uh, Sine of e to the negative x over e to the 2x dx. E to the 2x on the bottom becomes e to the negative 2x on top, sine of e to the negative x dx. So let e to the negative x equals u, then the derivative is negative e to the negative x dx is equals to du. This is just e to the negative x twice. So we can put that and that here to get negative du. So you get the integral, the negative du here. Uh, because e to the negative x dx is equals to negative du. So the residual e to the negative x is going to be u, and then the e to the negative x inside sine is going to be sine u. We use the di method for here. For here, the first one is negative, so let's put that. Let's be aware of the negative. It's negative here, since it's negative here. So the next one is positive, then negative. So this is going to be u, 1, 0, sine of u, then negative cosine of u, then negative sine of u. Diagonals, we get negative, negative, positive u, cosine u, positive, negative, negative, sine of u. U is again e to the negative x, so this becomes e to the negative x cosine e to the negative x minus sine of e to the negative x plus c. This is the answer. All right. 28. E to the 2x sinh 3x. So again, di method, just the di for the integration by parts. So e to the 2x sinh 3x. First one is 2 e to the 2x, and then cosh, 3 cosh 3x, chain rule and stuff. 4 e to the 2x here, then 9 cosh 3x here. No, actually, I'm wrong here. Sorry. Hold on. It's actually 1/3 since it is the integral. This is 1/9 now. Sinh, sorry. Again, another mistake. Sinh. I'm sorry about the mistakes. So, what we do here is this. The diagonals. So, e to the 2x cosh as 3x over 3 minus 2 over 9, then e to the 2x sinh 3x. So, the next step is to integrate this entire thing. So plus integral of 4 over 9 times e to the 2x sinh 3x dx. So in order to remove this, we have to subtract this by 4 over 9, whatever the integral is. So minus 4 over 9 integral. I can't be bothered to write that. So that cancel. 1 minus 4 over 9 is basically 5 over 9 times the integral is equals to e to the 2x cos 3x over 3 minus 2 e to the 2x sinh 3x over 9. And then we multiply both sides by 9 over 5 to make sure that this is gone. We get the integral of e to the 2x sinh 3x is equals to, multiply this by 9 over 5 as well. So 3 and 9 cancel each other out. This becomes 3. So it becomes 3 e to the 2x sin cos 3x over 5 minus 9 and 9 cancel becomes 2 over 5. And then e to the 2x sin 3x. We have plus c here, and that's the integral. That's long, but hey, it's worth it. Next. X secant x tangent x. For this one, you really need to know your derivatives, integrals. So di, then we put x here, and then the rest. Secant x tangent x here. Now, what function do you know has the derivative of secant x tangent x? Let's put the derivative of x here. Well, the answer would be secant x. And what's the integral of secant x? We discussed this earlier. This is ln of secant x plus tangent x. It's out of order, but whatever. So we get diagonals here. X secant x minus ln of secant x plus tangent x. Let's see. Oh, it's the messiest rectangle I've ever drawn. And that's it. 30. I'm going to rest out it. So 30 is square root of x e to the square root of x dx. So for this one, let the square root of x be equal to u. Now, you could find the derivative of both sides immediately, but what I like to do is to square both sides. We get x equals u squared, then find the derivative of that. Dx is equals to what is the derivative of u to u squared? 2u, then dv. So basically, dx becomes 2u u, and then square root of x here becomes u, then e to the u. Rearranging, we get uh uh 2u squared e to the u du. Di method here, so we get u squared here, and then e to the u here, plus minus plus minus. Then derivative of u squared is 2u, derivative of 2u is 2, derivative of 2 is 0. And then e to the u all the way. So u squared, e to the u, and whatnot. First one is going to be, well, we multiply this by 2, so 2, then u squared e to the u, minus 4u e to the u, plus 4 e to the u, and then that's it. 2 u squared becomes x. U is e to the square root of x. Minus 4 square root of x e to the square root of x. Plus 4 square root of, no, e to the square root of x. Plus c. So that's going to be the answer. All right, that's question number 30. I'll see you on question number 51. We will now proceed with the next question, question number 31. The integral of secant cubed x dx. Now for this one, we can't use any substitution straight away, but we can do this first. So what we need to do is to separate this into two parts. Secant squared x times secant x dx. Why? Because we can use integration by parts here. Let's set it up. Okay, for secant, this becomes secant x. For secant squared, here it is. Derivative of secant x is secant x tangent x. The integral of secant squared x is tangent x. We didn't need this one. So the result would be diagonal. So secant x tangent x minus the integral of secant x tangent squared x dx. Now, remember, secant squared x minus tangent squared x is equals to 1. And isolating tangent squared x, we will get Tangent squared x is equals to secant squared x minus 1. So we will use that. This becomes a secant x tangent x minus uh, secant x and then multiplied by secant squared x minus 1 dx. So expanding, we get secant x tangent x minus integral of secant cubed x minus minus becomes plus secant x dx. Let me just put divider here. There we go. So in these situations, we can actually separate the integrals together if they're separated by a plus. So we can do something like this. Secant x tangent x minus integral of secant cubed x plus integral of secant x dx. We know this. This is just ln of secant x plus tangent x. And this is the same as this. So we get, let's abbreviate that as I for integral. So we move it to the other side, becomes 2i. This becomes secant x tangent x plus ln, absolute value, secant x plus tangent x. Now, we just divide both sides by 2, right, like that. So this is gone. I is equals to 1 half secant x tangent x plus 1 half ln secant x tangent x. This is the answer. We're actually trying to find I. I is the integral that we're trying to find. So uh, there you go. That's your answer. And don't forget to circle or box that in so the professor knows that's the answer. Question number 32. Integral of sine 5x cosine squared x dx. Now, you need to experiment with different approaches and on how to do this. So maybe you can try integration by substitution. Maybe if sine x is equals to u, cosine x dx is equals to du. Oh, we do have another cosine here, and uh, cosine x in terms of sine x not really a pretty thing to behold. It's not doesn't have a nice value. So maybe not that. Maybe if we try um rewriting this as 1 minus sine squared x, but it would be like sine to the 5x minus sine to the 7x. So that is even worse than I uh than the original thing. What about we do this? We separate a single sine x and then sine to the power 4x, then cosine squared x. This is also sine squared x to the power 2. So sine squared x squared, something like that. So we know sine squared x is 1 minus cosine squared x, and then just putting squared in that, and putting the rest here. And I think we have the conditions that we need in order to get integration by substitution. So if we let cosine be u, negative sine x dx is du. We have sine x here, we have dx here. Just multiply -1 to both sides, we get sine x dx is equals to, negative du. So we can substitute everything in. We get negative, then at the end, negative du, parentheses, all right? So 1 minus, this cosine squared x becomes u squared. Uh, this squared, of course, then times u squared here. Now, all we need to do here is simple algebra. We just put negative outside because it's just a constant multiple, and we expand this. This becomes 1 minus 2u squared plus u4. So, and then we multiply by u squared. So this becomes u squared minus 2u4 plus u to the 6 du. Right. The answer will become negative u cubed over 3. All right. The negative negative becomes positive 2 u to the 5 over 5 a negative, and then minus u to the 7 over set. Bring back cosine x here. We get negative cosine cube x over 3 plus 2 cosine to the power 5u over 5 minus cosine to the 7. No, not ux. Sorry, let me just x over 5 plus 7 plus c. And this is the answer. This entire thing is the answer. All right. Question number 33. Cosecant to the power 4x. What do we know about cosecant? Well, we know that it's cosecant squared x minus cotangent squared x is equals to 1. Uh, this is less familiar than this secant squared x minus tangent squared x, but this is a bit similar to that, right? So, what do we do here? Well, let me write the x here. Well, let's separate this into two. So this becomes cosecant squared x, then cosecant squared x. Let's multiply two those. This can become, well, this is just 1 plus cotangent squared x. So that's what cosecant squared x can become. So we can turn this into 1 plus cotangent squared x, and then cosecant squared x here. What can we do after this? Well, we know that the derivative of cotangent x, that is equal to negative cosecant squared x. So we can we can substitute cotangent x to be u, and we are left with negative cosecant squared x. The x is equals to the u. Now the negative we need to remove that because we have no negative here, so we just multiply by both sides by -1. So we get cosecant squared x dx equals negative du. So this is now replaced with negative du, parentheses of course. So and then 1 plus cotangent squared x becomes 1 plus du squared. So the negative can go outside, and then uh the integral of 1 is just u. The integral of u squared is u cubed over 3. Alright? So we distribute the negative, and then this is immediately cotangent x plus, no, minus, sorry, minus cotangent cubed x over 3. And then we have plus c, and that's the answer. Alright, it's nice. Question number 34. The integral of 2 plus cosine, oh, no. Integral of 1 plus 2 cosine x over 2 plus secant x, and then the x. So this is one of those questions that looks hard, but you need a little bit of experimentation in order to get to the point where you can solve this. So what can we do here? Well, let's try multiplying both the numerator and the denominator by cosine. Because look at there is a secant here. Ugly. I don't want that secant here. So why not multiply both the numerator and the denominator by cosine? Let's see what we can get. So we multiply by cosine x on both the numerator and denominator. We get, let's just put cosine x here. Then 1 plus 2 cosine x over, let's put the integral sign here, and then the x. There we go. Over, then cosine x times 2 becomes 2 cosine x, and secant x times cosine x becomes 1. 1 plus 2 cosine x, 2 so cosine x is 1. This and that cancel each other out. Becomes cosine x dx. So from something that looks very complicated, it's now a simple thing. Cosine x dx. We know the answer to that. It's just sine x plus c. That is the answer. That's it. Simplifying it is really good. Question number 35. the integral of cotangent x over cosine squared x dx. When I hear cosine squared x on the bottom, something like this, I immediately think of secant squared x because the integral of secant squared x is just tangent. So maybe there's something there. So let's try that. So this is now the integral of secant squared x, then cotangent x. Cotangent reminds me of tangent, which is 1 over, this is just 1 over tangent, right? So, tangent, secant squared, they mix very well. So, let's put cotangent down. So, this becomes secant squared x times 1 over tangent x dx. Look, we have tangent, we have secant squared x. We can use u substitution or integration by substitution here to get let tangent x be u. The derivative of tangent x is secant squared dx x dx, and then derivative u is just 1 u. Secant squared dx. We have that. So that becomes du. Tangent x is now u, so this becomes 1 over u. And look, we have 1 over u, and the integral of that is just ln of u. And we can substitute back x here, so we get ln of tangent x. Let's see. It's the answer. All right, that's it for the trigonometry. We are on to exponentials stuff. So question number 36. Oh, this is surprising. X to the x over ln x dx. Now this looks hard. This looks like it doesn't have an answer, but it actually has an answer. Before that, let me talk to you about something that don't have answers. X to the x dx. You may think it has an integral that's very long. This does not have an integral. No elementary anti-derivative. So if your professor asks you what is the integral of x to the x, just tell him there's no answer. It's been proven. But this looks more complicated, but it has an answer. Recall, e to the ln x is equals to x. We just cancel e and ln because of the function inverse property. Remember, f inverse of x is equals to x. All right. So this is true. And we can also recall that a to the b and then to the c is equals to a to the bc. Those are exponential rules. So you might remember them. So we can actually change x here to be e to the ln x. So how do we do that? Like this. E to the ln x and then to the power x over ln x. Again, we can multiply the powers here. So ln x times x over ln x. This and that cancel. We are left with e to the x dx. And what's the integral of e to the x? E to the x plus c. Or you can also write the answer to be x to the x over ln x plus c. I don't know. Pick one, I guess. But there's the same thing, so no problem there. This may be answer e to the x. You'll get extra points that way. Uh, question number 37. ln x squared. Not ln x squared. No. ln of x, parentheses, squared. You can also write this down as ln squared of x, much like how you would write in trigonometric notation. So you can do that. So how do we do this? Well, well, we can always use the integration by parts technique. Remember this one? Yeah. So this is where we put ln squared x, and then for the I, we just put 1. ln squared x times 1 is just ln squared x. So that can fit. The derivative of this is 2 ln x, and then chain rule over x. Then the integral of 1 is just x. This and that cancel each other out, so that's good. Let's find the integral first by diagonal multiplication. X ln squared x. Then we subtract by the integral of, well, this, the product of this, essentially. So the product of this, the x and x cancel each other out, we get 2 ln x dx. Now, now there's another problem, ln x. We don't know the integral to ln x. So let's do another integration by parts. Uh, well, for this one, let's just rewrite everything. So everything's here, minus 2, and then ln x. Put this in brackets so it's easier to illustrate. So we're just trying to find this. So ln x in here, 1 in here. Ln x times 1 is just 1. So the derivative of ln x is 1 over x. The integral of uh, 1 is just x. So this is x ln squared x. And then we subtract by 2 times x ln x. And then this becomes a negative, negative, positive 2. Then the integral of 1 over x times x. This is just 1. So this is going to be x ln squared x minus 2x ln x plus 2. Then the integral of 1 is again just x. Then plus c. That's the answer. Question numero 38. The integral of e to the x plus 1 over e to the x plus x. This is just a simple case of integration by substitution. Let e to the x plus x is equals to u. So the derivative of that side is e to the x plus 1 dx is equals to du. E to the x plus 1 is right here. So we'll just get a du over u. That is just u. Again, this is just ln of u. And we just substitute e to the x plus x back in. We get e to the x plus x. This can become negative, so this has to be absolute value plus c. That's the answer. 39. The integral of 39x to the power x dx. So 39 to the power x. Again, I said earlier, e to the ln x is equals to x. It also can apply to constants. So e to the ln 39 is just 39. So we can do that here. Integral e to the ln 39 times x dx. That also works. So let's do a little integration by substitution. But if you already know the answer, we did this earlier. You can already use the formula. But just for completion's sake, let x ln 39 be equal to u. Derivative of this is going to be ln 39 dx equals to u. So we only have the x here, no ln 39s anywhere else. So we just divide both sides by ln 39. And whoop, whoop. And then we got dx is equals to du over ln 39. So dx becomes du over ln 39. E to the ln 39 times x becomes e to the u. And then du over whatever here. And then this becomes eu over ln 39. U becomes e to the x ln 39 over ln 39. Now after this one, ln 39 we can put e to the ln 39 back to 39 to the power x over ln 39. And that is the answer. Next one. 40. The integral of x cubed e to the x squared dx. We did something earlier here, but we swapped x squared and x cubed this time around. So, but this is not that hard, right? By the way, another non-elementary antiderivative, uh, e to the x squared dx, or e to the negative x squared dx. These are non-elementary antiderivatives. So if someone's asking you to find the indefinite integral of this, refuse them because they are tricking you into doing it. But if you have definite integrals, there are ways you can solve this one, as you will see later. But that will come later. So stay tuned for that. Let's just put x squared be equal to u because making this into something easier to process like u is always good. So this becomes 2x dx equals du as usual. So let's separate this before we move on. X squared e to the x squared, then multiplied by x dx. We only have x dx, so we divide both sides by 2 in order to get x dx is equals to du over 2. All right? X dx. Bring that down. We get du over 2. The integral of x squared becomes u e to the, this becomes u and du. So let's bring the 1/2 to the outside. So we get 1/2 integral of u eu du. This we need the integration by parts. So we just put u in the derivative side. So derivative of u is 1 and then 0. So that's where we stop. E to the u, e to the u, e to the u. It's the same thing. So we just cross diagonal multiply and whatnot. So we get 1/2 times u eu minus e to the u. This substitute x squared back. We get 1/2 x squared e to the x squared. Sorry. Minus 1/2. I forgot 1/2 here. Sorry. 1/2 e to the x squared plus c. That's the answer. Next, let's do inverse trigonometric integrals. First, 41. The integral of 1 over secant x plus sine x tangent x dx. Now, this doesn't look nice, but maybe we can do a little bit of algebra, of trigonometric identities here. Let's try multiplying both the numerator and denominator by cosine, as we did earlier as well. So the numerator becomes cosine x. Denominator becomes, well, cosine times sine, secant x is just 1. And cosine x times tangent x. Remember, this is sine x over cosine x. So we just canceled out the cosine here. We get sine squared x. All right. Now, 1 plus something squared, that screams arctangent to me. So how about doing this? Let sine x equals u, again, u substitution. Cosine x dx is equals to du. Cosine x dx. That just becomes du over the top. Over 1 plus sine x becomes u, and then squared. And this is just arctangent of u. Um, let's substitute sine x back. We get arctangent sine x plus c. That's it. 42. The integral of arctangent x dx. So for this one, like the logarithm, we're going to be using the the integration by parts. So the DI method. The derivative of arctangent x and then just 1 here. Derivative of that is 1 over 1 plus x squared. Derivative of 1 is just x. So we get x arctangent x minus the integral of x over 1 plus x squared dx. So from here, let us make this 1 plus x squared be equal to u. Then derivative of this, we got just 2x times dx. Derivative is just du. We have x, but we do not have 2 here, so we just divide by 2 on both sides. X dx is equals to du over 2. Alright? So, x dx we have here So let's just put d over 2 here, then 1 over u. Let's just copy x arctangent here. 1 half here, 1 over u here. This screams ln of u. And then 1 half here, and then the minus. And then x arctangent x copy. Phew. So let's put things back into the x world. So x arctangent x minus 1 half ln of u becomes 1 plus x squared, which is always positive. So let's not worry about that. And there we go. Proceed. Nice. Next question. 43. Integral of e to the arc cosine x dx. That's it. Let me tell you another impossible integral. This is impossible. Impossible. It's another non-elementary antiderivative case. And it's been proven. It's not like we gave up and said it was impossible. No. It's already proven by some people back there that it is indeed impossible. So, what do we do? In here, well, this is much more possible. I'll show you. Arc cosine x, let's substitute that into u. Now, I don't want to derive this yet now. So, we will apply cosine to both sides. We get x is equals to cosine of u. Again, cosine are cosine, they're function inverse. And if you layer them on top one another, they cancel out. So that's why x equals to cosine u. Derivative of both sides. So dx is equals to negative sine u du. Our cosine x here, this becomes the integral of e to the u times negative sine u du. This becomes the negative integral e to the u sine u du. So we can use the integration of parts again here. Di. Put whatever you want, wherever you want it. So I want e to the u here and then maybe sine u here. Here is it's negative here, so let's put negative on the top. So alternating plus minus. Maybe that's where it ends. I don't know. So derivative of cosine is just cosine, and then derivative that's negative sine. Integral of e to the u is just you already know the drill. Diagonals, multiply that, and then integrate the bottom one. We get EU, negative EU sine u, plus EU cosine u, and then plus the integral of EU sine u. Look, EU sine u, we can bring EU sine u to the other side, so we get a negative 2 integral of e to the u sine u du equals to negative EU sine u plus e to the u cosine of u. So, what else? We just divide both sides by negative 2. Uh, both sides by negative 2. And we get the integral. No, actually, it needs to be negative. So just by negative 2. By positive 2, sorry. Because the original one had negative. So negative e to the u sine u is equals to uh just positive, sorry. Just divide by positive 2. So negative 1 half e to the u sine u plus e to the u cosine u 1 half. All right. Let's erase some things here. So after this point, what else? Well, there's sine of u, and u we know is cosine, r cosine x. So how do we interpret that? Well, we do know that cosine of arc cosine of x is equals to x. So we can draw a triangle here. The angle is arc cosine x. That's the analog for it. And the cosine of that is x over 1. So this missing side must be 1 minus x squared. So the sine of arc cosine x is what should be square root of 1 minus x squared over 1. So let's rewrite negative 1 over 2 e to the arc cosine x times 1 over, no, not 1, times square root of 1 minus x squared plus 1 half e to the arc cosine x times x plus c. That's your answer. All right, on to the next. Partial fractions. Okay. So the next technique we will be facing is the partial fractions decomposition. So watch this. So we need to find the integral of 1 over x squared plus 3x plus 2. Let's process the denominator first. So we get integral of 1 over x plus 2 x plus 1. You can check me on that, but that's the solution. So how do we partial fraction decomposition this thing? Well, this is the longer method. I'll show you the shorter method later. So this becomes a over x plus 2 plus b over x plus 1 x. What is a and b? That's what we'll have to find out. So let's add both of these together. So cross multiply first. So we could get a sense for what we need to do. Plus 1, let's multiply this one and then cross multiply. A times x plus 1 plus b x plus 2 dx. So let's go to the side and calculate a and b for a moment. We get first we get ax plus a plus bx plus 2b. This is 1 because look, the denominator here match. The numerator should match as well. So this has to be 1. All right. Are there any x terms? No. So this will be 0. Are there any constant terms? Yes. So this becomes 1. Now this is just a matter of systems of equations, simultaneous equations, whatever you call it. So we subtract first. So we get b minus 2b is negative b. 0 minus 1 is negative 1. This means b equals 1. So substituting it here, we get a plus 1 equals 0. This means a is equals to negative 1. So we can equate this to a is negative 1 now. Negative 1 over x plus 2 plus b is 1. So 1 over x plus 1 dx here. All right. So this and that easier to solve because this looks like an ln x situation. So this becomes x plus 2 becomes negative ln of x plus 2. All right. And if you want to double check it, just try thinking of the derivative of this. Derivative is 1 over x plus 2 times the derivative of x plus 2, which is just 1. So no problem there. Plus, again, another ln of x plus 1. And then plus c. That's the answer. So that's the partial fraction decomposition trick for these kinds of equations. So you should probably understand how it works first. And then we can get to the shortcut later. For now, question number 45. 1 over x cubed plus 1. Now, if this was x squared plus 1, that would be just an easy arctan, but it's not. So we'll have to do something scary. So here's what we do. Yeah, yeah, very scary. This one. So don't freak out. Don't freak out. First, uh, first off, you get what is x cubed plus 1? Well, you can break that into x plus 1, then x squared plus x minus x plus 1. And the x is already there. So that's the bot. Now, let's partial fractions this thing. So we get a over x plus 1 plus for x, the x squared minus x plus 1. Since this is squared, the top has to be bx plus c, right? Not just b, but bx plus c, so that we're complete, right? So for example, there's x cubed term below when you want to partial fractions that, it should be bx squared plus cx squared, cx plus d or whatever. But basically, the highest term on the top has to be just one term lower. So you need that. All right. So uh, let's just cross multiply. We get ax squared minus ax plus a plus bx squared plus bx plus cx plus c. All right. Since cross multiply, this has to equal to 1. Since earlier it was just 1. So let's combine the x squared terms, a plus b. Are there any x squared terms in the original? No, this is 0. Combine all the x terms, negative a plus b plus c. Are there any x terms in the original? No, 0. Combine all the constant terms, a plus c. Are there any constants in the original? Yes, that's 1. All right. So how do we solve this? Just some simple stuff, but you might have to get creative around it in order to really get at the nitty-gritty of it. So let's do this first. Label them 1, 2, 3, so we can keep track of which is which, you know? So let's add 1 plus 2, just out of morbid curiosity. And since a plus minus a is 0, so maybe we can start somewhere there. So we get 2b plus c is equals to 0. Label this as 4. Next, we subtract 4 by 3. So how do you subtract 4 by 3? Well, 4, so 2b minus anything here, nothing, so just 2b. Uh, c minus c becomes 0, and then 0 minus a becomes negative a, okay? And then, since we subtract 4 minus 3, we also make 0 minus 1, so negative 1 here. So label this as 5. A and B. 5 plus 1. Let's add 5 and 1. Uh, negative A plus A is 0. So ignore. 2B plus B is 3B. And 0 plus negative 1 is negative 1. B is now equal to negative 1 over 3. Going back, we can solve for C here. So negative 2 over 3 plus C is equals to 0. C becomes 2 over 3. Negative 2 over 3 minus a is equals to negative 1. Uh, move this to the other side. This becomes plus 2 over 3. This becomes negative 1 over 3. Negative a is equals to negative 1 over 3. A is equals to 1 over 3. So, yeah, how about that? So we now have A, B, and C. Let's put it back. Put it back, you know. Uh, A is 1/3, so 1/3 over x plus 1 plus b is negative 1/3 x plus c. C is 2 over 3 over x squared minus x plus 1 dx. Let's multiply all of it by 1/3. Let's put 1/3 on the outside since all of these are divisible by 1/3. So this becomes the integral of 1 over x plus 1 uh minus, let's put minus outside here. So this becomes x plus minus 2 oh, over x squared minus x plus 1 dx. All right. This is getting longer, in it. Don't worry, it just gets longer. All right. Uh, Don't worry about it. So we just put everything. Um, Before we continue, let's just copy this thing. So for the next one, 1 over 3, having trouble in here, sorry. 1 over 3 integral of 1 over x plus 1 minus x minus 2 over x squared plus x minus x plus 1 dx. Yes, that's consistent. So that's the partial fractions thing we saw earlier. This one is easy enough. This one, not so much. So let's separate these together. You get 1/3 integral of 1 over x plus 1 minus 1/3 integral of x minus 2 over x squared minus x plus 1. How about we multiply this by 2? So 2 and then 2 here. So we multiply both numerator and denominator by 2. Let's ignore this for now and focus on what's going on here. All right. So let's focus on that because this is much more difficult to deal with. So 1/2 we can bring outside. So this equals 1/6 integral and then 2x minus 4 over x squared minus x plus 1. Now the derivative of the bottom is 2x minus 1. This is 2x minus 4. So I have to separate 3 from here. So let's do that. Let's do exactly that. 1 over 6 and then 2x minus 1 over x squared minus x is 1. Then minus 3 times minus 3 over x squared minus x plus 1. Yes. This one, we can use U substitution and whatnot, but let's focus again on this one first. It seems like it's not ending, but it will end somewhere. Huh. So now we end up with, actually, let's separate these two together. Minus 1 over 6. There you go. Let's separate these together. So this and that cancel out. So then we get square. So 1/2 integral of 1 over x squared minus x plus 1. If we complete the square, we get, uh, well, x squared minus x plus 1 over 4 minus 1 over 4 plus 1. 1 over 4, this becomes 3 over 4. This becomes x minus 1/2. It's quantity squared. So that's called completing the square. So let's put that on the denominator, but we'll do something else. 1/2 squared. And then we add by the square root of 3 over 2 quantity squared. All right? Confused yet? I am. So what we have to do here, calm down. What we have to do here is to, oh God, is to multiply the denominator and the numerator by this in order to get rid of it. So the reciprocal, something like that. Squared. So this becomes just 1, 1, plus, then let's just flip it so it's easier to see. And then maybe 2 over root 3, then multiplied by x minus 1/2, and then squared on the outside. On the top should be 4 over 3, something like that. Dx. All right, let's go to another layer. God, this is getting longer, eh? 1/2 integral of uh 1 over, oh, no, no, no. 4 over 3, or let's just put 2 over root 3 here, squared, over 1 plus 2 over root 3 x minus 1 half plus, not squared, squared, dx. Oh, okay. So let the inside, this 2 over root 3 x minus 1 half, this be equal to u. Finally, we're doing substitution, something familiar. So the derivative this is this root 2 over root 3 dx, since this is just a constant, so x is the only thing important, du on the other side. And look at here, we do not have 2 over root 3. Oh, we do have 2 over root 3 here. How silly. So one of the 2 over root 3's is going to be sacrificed, one of them will place outside. Right. Uh, 2 over root 3 dx over 1 plus 2 over root 3 x minus 1 half quantity squared. There you go. Right. So this becomes du. This and that cancel. We got 1 over square root of 3 outside, and then 1 over 1 plus u squared inside. This becomes 1 over square root of 3. Uh, arctan of u. Uh, okay. So this becomes now 1 over root 3 arctan of 2 over root 3 x minus 1 over root 3. I just distributed this for clarity. All right, let's go back to here. This one. Let's bring let's bring it back. 2x minus 1. Let's bring 1 over 6, 2x minus 1 over x squared minus x plus 1. You can use the integration by substitution for this, but I know that uh, integ the derivative of x squared minus x plus 1 is just 2x minus 1. And since that is an integral derivative over function, this is an ln situation. So I'm gonna already go straight to ln of x squared minus x plus 1. You can check using integration by substitution, but that's essentially. And the third one. The third one is 1 over 3, 1 minus 1 over 3 integral of 1 over x plus 1. Is it correct? Yes, 1 over x plus 1. Okay, this is just ln x. All right. So let's assemble the cake because we need to eat that thing. Okay, ladies and gentlemen, the integral of 1 over x cubed plus 1 is equals to 1/3 ln of x plus 1. Is it plus or minus? Hold on. Minus 1 over 6 ln of x squared minus x plus 1. Hold on, let me check. Uh, plus, and let's put it on the other side, there's no space. Plus 1 over square root of 3 arctangent of 2 over square root of 3 x minus 1 square root of 3 plus c. It's so long. Who knew? You know? There are much longer integrals in here. Derivatives, they're short and sweet. Integrals, man, they get long and uh, and difficult, you know? Question number 46. Cut. Cosine x dx over 7 minus 5 sine x minus cosine squared x. I see cosine squared x here. I think of 1 minus sine squared x. So let's back it up. So using the identities, we get 7 minus 5 sine x minus 1 minus cosine squared x. Dx. No, dx is already there. All right, dx again. All right. So 7 minus 1 is 6. Minus, well, no, not cosine squared x, sine squared x, sorry. This becomes sine. Minus 5 sine x plus sine squared x. Let's rearrange this into something much cleaner. This is now a quadratic equation. Sine squared x minus 5 sine x plus 6. Now, we could use integration by substitution first here. Let sine x be equal to u. Cosine x dx is equals to du. So we get du over u squared minus 5u plus 6. Uh, using partial fractions here, we get du over u minus 3 and u minus 2. So the other method we have for hold on, let me just move this one. There. The other method we have for partial fractions is much easier. So here's the procedure. Let's split this again into a and b. So we got a over u minus 3 plus b over u minus 2 du. All right. So for first we find a. Before we find a, we just do this. U minus 3 is equals to 0. What should be the value of u? Well, u equals 3. All right. After that, we sorry. After that, we just substitute u equals 3 to the rest. So b no no. So earlier we had 1 over u minus 3, u minus 2, right? Let's delete u minus 2 here and then substitute 3 into the u. So 1 over 3 minus 2 equals 1. So a equals 1. For b, u minus 2 is equals to 0. U equals 2, right? So 1 over u minus 3. That's where we substitute it. So we get 1 over 2 minus 3. This is negative 1, which is what b is now. So now that we have that, let's substitute a and b into the original places. So 1 over u minus 3 plus, and minus, sorry. This is now minus 1 over u minus 2 du. This becomes ln of u minus 3 minus ln of u minus 2. This becomes ln of, u is sine x earlier. Sine x minus 3 minus ln of sine x minus 2. Yeah, plus c. Hold on. Um, oh, no, 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 that's correct. That's correct. I was wrong earlier. Next question. 47. Oh, no, not another long one. Damn, this is a lot. Okay. 1 over x to the 4 plus 4 dx. Well, so we can x to the 4 plus 4, we can actually do this. X to the 4 plus 4. We just add 4x squared and then subtract 4x squared here. This is x squared plus 2, comma squared, minus 2x, comma squared. So just difference of two squares, x squared plus 2x plus 2, and x squared minus 2x minus 2, plus 2. So that's the two things. So uh, 1 over x squared plus 2x plus 2, x squared minus 2x plus 2, x integral. All right. So, partial fractions, this thing, ax squared, uh, no, sorry. Partial fractions, we get ax plus b over x squared plus 2x plus 2 uh, plus cx plus d over x squared minus 2x plus 2 dx. All right. I'll just expand it first. So ax cubed minus 2ax squared plus 2ax plus bx squared minus 2bx plus 2b plus cx cubed plus 2cx squared plus 2cx plus dx squared plus 2dx plus 2d. All of this is equals to 1, the original number here. So this is now a system of four equations. A plus C is 0. Negative 2A plus B plus 2C plus D, 0. 2A minus 2B plus 2C plus 2D, 0. And 2B plus 2D is equals to 1. I'm not going to tell you everything here because if I did, we would be here all year and like still 10. So, uh, let's just cut to the chase. A is 1 over 8. B is 1 over 4. C is negative 1 over 8. D is 1 over 4. If it's wrong, feel free to double check me. I will answer to that. Right. So let's put it back into the original stuff. The integral of 1 over 8x plus 1 over 4 over x squared plus 2x plus 2 plus negative 1 over 8 x plus 1 over 4 over x squared minus 2x plus 2. Let's put 1 over 8 to the outside. No. Let's put 1 over 16 to the outside. What would that do? Well, this becomes 2x plus 4. And then minus, let's subtract now. So 2x minus 4 over x squared minus 2x plus 2. So now, let's separate the easy ones from the hard ones. Because 2x plus 2 is easy to integrate. It's ln or ln and whatever. Minus 2x minus 2 over x squared minus 2x plus 2. Those are just ln situations, so no problem there. Natural logarithms and whatnot. Uh, then we add the remainders. 2 over x squared plus 2x plus 2. And then here it's minus 2 over x squared minus x 2x plus 2. Let me check if this is correct. Oh no, actually this is positive. Check. Yep, it is possible. So, what do we do now? Let's focus on these two first. So, complete the square. On the one here, 2 over x plus 1 squared plus 1 is x squared plus 2x plus 2. Everybody knows 1 plus 1 is 2, but I know 2 is 1 plus 1. Someone wise told that to me on over the internet. And the other one is just 2 over x squared, no, not x squared, minus 1 squared plus 1. So simple. X plus 1, x minus 1, the derivative is just 1. So we don't have to use integration by substitution. So we know this is just arctangent through and through. So will be the final answer. Ladies and gents, hold your horses because it's going to get rough. Hold on. All right. Looky here. Wait, this is the integral of everything, and everything just got cut off. Sorry about that. Ladies and gentlemen, the integral is no, hold on. Before we proceed, ladies and gentlemen, the integral of 1 over x to the 4 plus 4 dx equals to 1 over 16. This is just an ln situation. All right, nice. Minus, this is another ln situation. 1 over 16 ln of x squared minus 2x plus 2. Good. This is an arctan situation as we showed. 2 arctan of x plus 1. There's no the derivative of x plus 1 is just again 1, so it doesn't affect the entire thing. Plus 2 arctangent of x plus 1, minus 1. Plus c. There you go. That's it. That's much easier than the cube, but still hard. Needed an extra star still line. So there we go. 48. Oh god, I wanna stop doing partial fractions. Anyway, 1 over x plus 1. It would be easy if that's just the integral, but no. There's also x plus 4 and 2x plus 3 dx. Separate all these together. We get a over x plus 1 plus b over x plus 4 plus c over 2x plus 3 dx. Here's what we do. How do we do the shortcut? So for a, what's the denominator of a? X plus 1. Equate that to 0. X is now equal to negative 1. All right? The rest. Look at the rest. 1 over x plus 4, 2x plus 3. That's going to be the rest. So just put negative 1 in all of them, and all of the x's. Negative 1 plus 4, and then 2 times negative 1 plus 3. So this becomes 3. This is negative 2 plus 3, which is 1, 1/3. For b, x plus 4 is equals to negative 4. 0. Why am I doing this? 0. X is now negative 4. What is the rest? X plus 1, 2x plus 3. All right. So we just put negative 4 into everything. So 1 over negative 4 plus 1, and then 2 times negative 4 plus 3. This is negative 3. This is going to be negative 8 plus 3, negative 5. So 1 over 15. Yep. C, 2x plus 3 equals 0. X is now negative 2/3. Oh, sorry, 3 over 2. I should do this mistake. 3 over 2. All right. The rest is 1 over x plus 1, x plus 4. Substituting, we get 1 over negative 3 over 2 plus 1. Mamma mia. Negative 3 over 2 plus 4. 1 minus 3 over 2, this is negative 1 half. This is 8 minus 3 all over 2. This is going to be 5 over 2. So it's going, the bottom is going to be 4, the top is going to be 5. So just, uh, the reciprocal is negative 4 over 5. So that's going to be A, B, and C. So let's do this. Uh, where do we put it? All right. Let's put it in before we move anything. Might we forget everything. So, 1 over 3 over x plus 1 plus 1 over 15 over x plus 4 minus 4 over 5 over 2x plus 3. And that is the integral we're trying to find. All right. Let's move everything up. Jesus. Here we go. Let's separate everything so nothing gets lost. Oh, this becomes 1/3 integral of 1 over x plus 1 dx. Plus 1 over 15 integral 1 over x plus 4 dx. Minus 4 over 5 uh, integral of 1 over 2x plus 3 dx. Now, the derivative of 2x plus 3 is 2. So, we need to multiply this by 2. We also need to divide by 2. So, we just multiply by 1 half outside. Cross multiply, we get 2/5. So, 1 over 3 ln of x plus 1 plus 1 over 15 ln of x plus 4 minus 2 over 5 ln of 2x plus 3 is our answer. Plus C, don't forget. Next question. Question number 49. Integral of 1 over x squared minus 1. Yes. This, my friends, is just 1 over x plus 1, x minus 1 dx, which separating it becomes a over x plus 1, a over x minus 1, no, b. Let me erase that. This becomes b. Dx. All right. For a, uh, x plus 1 equate to 0, x negative 1. All right. So the rest is 1 minus x minus 1. This becomes 1 over negative 1 minus 1, negative 1 half. B, equate x minus 1 to 0. X is now 1. The rest is 1 over x plus 1. So this substitute x equals 1. So 1 plus 1. This becomes 1 half. Good. Put everything back. We get 1 half over x plus 1 plus, oh no, the negative 1 half plus 1 half x minus 1. All right. So, okay. So let's put 1 half outside. We get negative 1 over x plus 1 plus 1 over x minus 1. Yep. Yep. So to solve this, we get 1 half, negative 1 half ln of x plus 1. It's going to be this one. And then plus 1 half ln of x minus 1 plus c. There we go. Let me just write that properly so you can understand and rearrange it. So the answer is 1/2. Let's put this first since it is positive. Minus 1/2 ln of x plus 1 plus c. Just rearranged some stuff. There you go. That is this one, and I'll see you in the next part, in question 50. Right? Moving on. We will be doing something called trigonometric substitution, or trig sum, as some of you may know. So, before we start, let us remember the three main Pythagorean identities, which is sine squared theta plus cosine squared theta is equals to 1. And from there, we can conclude that uh, secant squared theta minus tangent squared theta is equals to 1. And also, cosecant squared theta minus cotangent squared theta is equals to 1. And we can use these throughout our adventure in Trig Sub. So let's try that we'll be using one of these. So our first problem is actually very similar to the previous problem in question number 49, which is the integral of so 50 is the integral of 1 over x squared minus 1. It's not just very similar. In fact, it's the same problem that we do have. So, uh, what can we use here in order to solve this? Hold on, sorry. Well, let's return to one of them. I'm thinking secant squared theta minus tangent squared theta is equals to 1. Hmm. Maybe I can put tangent to the other side. So secant squared theta is equals to 1 plus tangent squared theta. That's not quite right. What about I subtract 1 from both sides? We end up with secant squared theta minus 1 is equals to tangent squared theta. So, what now? Well, secant squared theta minus 1 is something squared minus 1. This is also that something squared minus 1. So we can substitute secant theta here for x. So the first step is to substitute x as, so we will let x equal to secant theta. Then find the derivative of both sides. Derivative of x is dx. Derivative of secant theta is secant theta tangent theta d theta. All right. So we can replace everything in the original these with these substitutions. So on the below, we get secant squared theta minus 1, then multiplied by dx, which is now secant theta tangent theta d theta. This is now tangent squared theta. All right. We have tangent theta in the numerator, tangent squared theta in the denominator. We can cancel one of those. We end up with the integral of secant theta over tangent theta d theta. All right. So secant theta is also 1 over cosine theta, and tangent theta is also sine theta over cosine theta. We can multiply both the numerator and denominator by cosine theta. We can cancel cosine here, cosine here. We end up with 1 over sine theta or cosecant theta d theta. We got d theta here. So from here, we should be familiar with the integral of cosecant because it's very similar to secant, but let's do it one more time so we don't. So we know that the derivative of cosecant x is somewhat similar to secant, but it's negative. Cosecant, uh, let's do theta instead. Let's replace it with theta so we can be consistent. So the derivative of cosecant theta, also here, is a negative cosecant theta cotangent theta, and there you go. So the derivative of cotangent theta is equals to cosecant squared theta, but negative. So what can we do in order to find find the integral of cosecant theta? Well, what we can do is actually multiply both the numerator and the denominator by this. Cosecant theta minus cotangent theta. You will see why in a bit. Cotangent theta. And remember, we can cancel that in order to go back to the original cosecant theta. We need to distribute this. We will get uh, the integral of cosecant squared theta minus cosecant theta cotangent theta over cosecant theta minus cotangent theta d theta. So the derivative of cotangent is cosecant squared, negative cosecant squared. But this is negative, so this matches. And the derivative of cosecant is negative cosecant theta cotangent theta. So the derivative of the bottom is exactly the top, which is good because much like in uh the one in sine, we can also use this in order to use integration by substitution. So let's substitute again. Or we can shortcut it and say that this is just ln of the bottom. But let's just substitute it for good time's sake. So let cosecant theta minus cotangent theta be equal to u. We haven't used u yet, so it's fine. So this becomes negative cosecant theta cotangent theta minus negative negative is now positive cosecant squared theta and then parentheses and then d theta is equals to du. All right. And then after that, we can go back to the original equation and then we see that the top is can be replaced by du over cosecant theta minus cotangent theta is now u. This is 1 over u or ln of u or ln of cosecant theta minus cotangent theta. But hang on, isn't this all supposed to be in x? So let's go back to what theta means. So we remembered earlier that secant theta is actually equal to x over 1. So we can use the triangle again in order to find what the others are. So we have secant here, which is 1 over cosine, or 1 over cosine, or if we put the reciprocal of this, cosine theta is equals to 1 over x. This is the reciprocal of both sides. So cosine theta is adjacent 1 over hypotenuse x. So this should be x squared minus 1, or square root of x squared minus 1 by the Pythagorean theorem. So cosecant is 1 over sine theta, that's cosecant. So it should be the reciprocal of whatever sine is. The sine is the opposite over hypotenuse. So cosecant should be opposite, hypotenuse over opposite. So it's x over square root of x squared minus 1. So that's the first one. ln of x over square root of x squared minus 1. Minus cotangent is adjacent over uh, opposite. So it's 1 over square root of x squared minus 1. There we go. We could use plus c here, but I will refine this even further if you allow me. So we can combine this into one big thing, which is going to be ln of x minus 1 over square root of x squared minus 1. We can separate this into ln of x minus 1 minus, since this is the denominator, ln of square root of x squared minus 1. The square root can be put outside because it is basically to the power 1/2. So we get ln of x minus 1 minus 1/2 ln of, then x squared minus 1 can be expressed as the following, x plus 1, x minus 1. So we get ln of x minus 1, which we already have, minus 1/2, and then we can separate the ln of x plus 1 minus 1/2, then the ln of x minus 1. If we look here, ln x minus 1, ln x minus 1, they have, uh, say the same terms, but different coefficients. So we can add them together in order to get, well, 1, this is the coefficient is 1. 1 minus 1 half is just 1 half. ln of x minus 1 minus 1 half of ln of x plus 1. And that was the answer earlier, and that is the answer now. Let's see. So we see two different tactics, two different strategies to the same answer. So you know it's correct. All right. Enough about that. Let's use the trig sub on something else. The integral of 1 over 9 plus x squared. Now, what can we use here? Well, how about uh, secant squared theta minus tangent squared theta. How about that? Because I know there is addition somewhere in here. 1 plus tangent squared theta. Aha! There is 1 plus something. This is 9 plus something. Well, if we multiply 9 to both sides here, we get 9 secant theta, squared theta, sorry. Because 9 plus 9 tangent squared theta. And look here, it's 9 plus something squared, 9 plus something squared. We can use this. So what is this squared? We need this to be something squared. Well, the square root of this is just 3 and then tangent theta. So that's what we're going to be uh so that's what we're going to be substituting x to. So x is now equal to 3 tangent theta. All right? So the derivative of that is going to be dx equals 3 times secant squared theta d theta. That's going to be the derivative. So this is dx. We replace that to be 3 secant squared theta d theta. And then we replace everything with what we have. So 9 plus, and then x squared is 9 tangent squared theta. That's what we wanted earlier, and that's what we get now. So again, we proved that 9 plus 9 tangent squared theta is equals to 9 secant squared theta. So let's make that. Let's substitute it. So 1 over 9 secant squared theta multiplied by 3 secant squared theta d theta. Secant squared theta, they cancel each other out. The 3's and the 9's, they can cancel each other out, but this will be 3. So we will be left with 1/3 times the integral d theta. So 1/3 is thrown outside and inside is just a 1. And the integral of 1 is d theta, just theta. Then over 3. Alright? What is theta? Well, we know theta is equals, 3 tangent theta is equals to x. So let's try isolating theta here. So dividing both sides by 3, we get x over 3 equals tangent theta. Then theta is equals to arctangent of x over 3. So that's going to be theta. So we have 1/3, I'll just put 1/3 here, arctangent of x over 3 plus c. That's the answer. Question number 52. The integral of 1 over x square root of x squared minus 1 dx. Now, some of you may recognize this as the derivative of arcsecant, but let's see if that's the case. So, see, I see something squared minus 1, and I'm thinking of secant again, because I know secant squared theta is equals to, uh, well, no, actually, no. Minus 1 is equals to tangent squared theta. Something squared minus 1, I know we can use secant here in order to get tangent squared theta. So maybe let's use that. So let's secant theta equals x. Same thing if x equals secant theta. It's up to you. The derivative of both sides. Secant theta, tangent theta, d theta, then dx on the other side. So we just replace dx with d theta. So with this actually. So we get on the far right, we get secant theta, tangent theta, d theta. All right. Then we can substitute everything in. So 1 over, this will be secant theta. and square root of secant theta squared theta minus 1. We already established that secant squared theta minus 1 is tangent squared theta, so let us substitute that. Secant theta, sorry. Then square root of tangent squared theta, and then secant theta tangent theta. Here's the best part. Secant theta cancel each other out. Tangent and the square root and the squared cancel each other out. There's a tangent left. Tangent cancel each other out. We're left with the integral of d theta, which is just 1 d theta. Integral of 1 is theta. What was theta again? Well, we know secant theta is equals to x. Therefore, we can also conclude that theta is equals to arc secant of x. So we can put that in. The answer will now be arcsecant of x plus c. That's the answer. So it is true. Derivative of arcsecant really is the function. All right. Let's go. Question number 53. Integral of the square root of 1 minus x squared dx. 1 minus something squared. That reminds me of sine squared theta plus cosine squared theta equals 1. Because if I isolate, for example, cosine squared, we get 1 minus sine squared theta, right? Also, if we do it with sine squared theta, it will become 1 minus cosine squared theta. So let's just use this one in order to solve this. So we first let x be equal to sine theta. We could also put cosine theta, but it's up to you. Let me know if you're correct. And so derive both sides. Dx is equals to cosine theta d theta, right? So we replace dx with cosine theta d theta, all right? That's important. And then how about this one? Well, this now becomes 1 minus sine squared theta, yeah. 1 minus sine squared theta is cosine squared theta, and it's under the square root, which means we can cancel the square root and the square out. So we get cosine times cosine is cosine theta times cosine theta, for clarity. So we get the integral of cosine squared theta d theta. So what is this now? Well, we can't directly integrate this, but we can do something easier to integrate, which is remember cosine 2 theta, not square theta, 2 theta. The double angle identity of cosine is cosine squared theta minus sine squared theta. There's cosine squared theta here. What's the one we're trying to find. But there's another term, sine squared theta. If only we had a way to make this appear. Hmm. Hmm. What can be a way to make it disappear? Of course, the Pythagorean identity. Maybe we can input minus cosine squared theta. Yes, because minus sine squared theta minus cosine squared theta, we can factor the negative one out. We get with sine squared theta plus cosine squared theta, which is 1. So yeah, we've essentially deleted the sine squared theta from this and just turned it into negative 1. But this is no longer the same as the original one. So we do have to add cosine squared theta uh, to to neutralize the negative cosine squared theta that we did add. So we end up with 2 cosine squared theta. This becomes 1 minus 1 cosine 2 theta. All right. So let's try isolating cosine squared theta. We get 1 plus cosine 2 theta equals 2 cosine squared theta. We can divide both sides by 2. The two cancel out. Cosine squared theta is now this thing. This is called the power reduction formula. So what it means is essentially we're bringing down a power to half of it. So because we can't solve cosine squared theta directly. So there we go. So what we can do now is to, hold on, is to try solving for this by using the uh, power reduction formula. So we get the integral of cosine squared theta is now this. So 1 plus cosine 2 theta over 2 d theta. Okay? So 1 half can be brought outside. Let's bring 1 half outside, and then 1 plus cosine 2 theta will be here. All right. The integral of 1 is just theta. So let's put 1 half outside. Theta plus, then the integral of cosine is sine, and then 2 theta here. And then since we need to counteract the chain rule, let's put 1 half here. So if we utilize the chain rule of 2 sine 2 theta, cosine 2 theta times the derivative of the inside, which is going to be 2. So we have 1 half to neutralize that. Anyway, distribute again. We have theta over 2 plus 1/4 sine 2 theta. Okay, sine 2 theta, we don't have a value. We know sine theta is equals to x. That's what we did earlier. So uh, this becomes theta over 2 plus, well, this is now 2 sine theta cosine theta. So we can cancel the 2 and the 1/4 out in order to get 1 half sine theta cosine theta. Mhm. All right. So we know that sine theta is equals to x. That's what we said earlier. So let's build a triangle here. This is angle theta. This is a right angle. So theta is sine theta is the opposite over the hypotenuse. So x over 1 here. Opposite should be x, and then hypotenuse should be 1. This is now 1 over 1 minus x squared. All right. And then uh, we can show the final answer. Theta is arc sine x. So this is 1 half arc sine x. Then we add 1 half sine theta is x, as we all know. And then cosine theta is the adjacent over the hypotenuse. So that it would be square root of 1 minus x squared over 1. So that's it. Then we add plus c, and that is the answer. For question 54, we have the integral of a square root of 1 plus x squared dx, which is similar to the question earlier, but the sign is now positive. So, how do we go about this? So, I remember earlier that secant squared theta is equals to 1 plus tangent squared theta. 1 plus something squared is exactly what we're trying to find. So, let x be tangent theta. See where that goes. So dx is equals to secant squared theta. That's just finding the derivative of both sides. So substituting everything in, uh, we get 1 plus tangent squared theta, substituting for the x, multiplied by secant squared theta d theta. This is equal to secant theta times secant squared theta d theta. Secant squared theta, that is going to be just secant cubed theta. And we had a secant earlier, a secant cubed earlier. The answer was 1 half secant theta tangent theta plus, or 1 half ln of secant theta plus tangent theta. So let's turn it back to x. How do we find tangent? Well, we know x is equals to tangent theta. Right? Oh, how do we do it? Secant, actually. So let's build the triangle here. Theta is the angle. So x over 1, this should be tangent theta. So tangent is the opposite over adjacent. So opposite should be x, adjacent should be 1. Hypotenuse is 1 plus x squared. Sounds familiar? Yes. So secant is, uh, we know cosine is adjacent over hypotenuse. So secant should be the reciprocal, hypotenuse over adjacent. So 1 half then hypotenuse over adjacent, or sorry, what hypotenuse? Hypotenuse 1 plus x squared. Adjacent is just 1. Multiply by tangent, which is by definition x, plus 1 half, then ln of square root of 1 plus x squared, which is secant theta, plus tangent theta, which is x. Let's rearrange this together. We get x square root of 1 plus x squared. Don't forget plus c, and we're done. All right. Question 55. Similar to the problem earlier, but now the signs are flipped. X squared minus 1 dx. Something is squared minus 1. This reminds me of cosine because it is actually no, I'm mistaken. Sorry. This actually reminds me of tangent squared theta, which is secant squared theta minus 1. Something squared minus 1. Well, let x be secant theta. Then dx becomes secant theta tangent theta d theta. Armed with this information, let's go into the integral. Substitute. Square root of secant squared theta minus 1. Dx is secant theta tangent theta d theta. This becomes, well, tangent squared theta. And since it is under the square root, we can cancel both the square root and the square root together, right? This becomes secant theta tangent squared theta d theta. Tangent squared theta is secant squared theta minus 1, as we saw earlier. So this becomes just distributed secant cubed theta minus secant theta. All right. So secant cubed theta we know is 1 half secant theta tangent theta plus 1 half ln of secant theta plus tangent theta. Right? Secant theta, the minus secant theta means minus ln of secant theta tangent theta, or plus tangent theta, sorry. The negative 1 half and the ln here, 1 half minus 1, negative 1 half. So this is 1 half secant theta tangent theta minus 1 half ln of secant theta plus tangent theta. Again, secant theta was equal to x, but we can also conclude that tangent theta, by square rooting this on the top, we get tangent theta is equals to square root of secant squared theta minus a 1. Uh, secant theta is x, so x squared minus 1 square root of that, and that is going to be tangent theta. Sound familiar? Yes. Look, it's right there. So, we get 1 half secant is x, tangent is square root of x squared minus 1, minus 1 half ln of secant is x plus tangent is square root of x squared minus 1 plus c, and that is the answer. Nice. Question number 56. 1 over square root of 4 minus x squared dx. Something minus x squared, I immediately think of cosine squared theta is equals to 1 minus sine squared theta. This is the Pythagorean identity that sine squared plus cosine squared equals 1. Rearranged. Multiply both sides by 4. We get 4 cosine squared theta equals 4 minus 4 sine squared theta. 4 minus something squared. This is 2 sine theta and then outside squared. That is something squared. So let x be 2 sine theta. All right. Dx then becomes 2 cosine theta d theta. D theta. Yeah. So substitute everything. We get 1 over square root of 4 minus 4 sine squared theta times 2 times cosine theta d theta. So this now becomes 1 over, this is now going to be 4 cosine squared theta, and it's under the square root, so it becomes 2 cosine theta multiplied by 2 cosine theta d theta. Cancel, 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 cancel. This becomes just d theta. All right. So after this, this becomes theta, just theta. What is theta? Well, sine theta, x equals to sine theta, right? So that means x over 2 is equals to sine theta. Then theta will now become arc sine x over 2. That's what exactly the answer is. Arc sine x over 2 plus c. All right. Last question for Trig sub 57. X over a square root of x squared minus 16. We can use something simple as like normal substitution, but let's use trig sub because that's the challenge. So I'm thinking of it should be something squared minus 16. What is something squared? Something is squared minus 1, something similar to that. How about secant? Secant. So secant squared theta minus tangent squared theta, just a reminder, is equals to 1. So secant squared theta, I'm just putting 1 to the other side, minus 1 is equals to positive tangent squared theta. So this could be secant. But 16, so we just take the square root of 16 secant squared theta, which is going to be 4 secant theta. And then we square that. We know this is 16 secant squared theta, which is what we do need here. So let x be no, not 16. 4 secant theta. Then dx will be 4 secant theta tangent theta d theta. Pardon my hard writing. There we go. So I forgot the x here. Sorry. Then we can substitute everything in. We get 4 secant theta on the top. Then square root of 16 secant theta minus 16 on the bottom. And then multiplied by 4 secant theta tangent theta. This becomes 4 tangent theta, right? Because of the square root and whatnot. So this becomes square root of 4 secant theta over 4 tangent theta times 4 secant theta tangent theta d theta. All right? Tangent, tangent, they cancel each other out. 4 and 4 cancel each other out. We are left with 4 times the integral of secant squared theta d theta. This is tangent theta. That is the derivative tangent, all right? So uh what is this in terms of x? Well, we can also look back here. We know x is equals to 4 secant squared theta. So maybe secant theta is equals to x over 4. Let's put it down here. Secant theta is equals to x over 4. So triangle again. Then this is theta. This should be x and this should be 4. And this is x squared minus 16. Right? So 4 tangent theta is just 4 times the, secant, which is now going to be, no, tangent, which is going to be is square root of x squared minus 16 over 4. Because that's what tangent is. 4 and 4 cancel each other out. We are left with x squared minus 16 plus c. And that's the answer. All right. Now on to some extra stuff. We are in the world of the Weierstrass substitution. So if earlier trig sub changed, for example, some rational or algebraic thing, and we turned it into trigonometry, now we're going to do the opposite. We turn trigonometry into something rational. How? Well, a man named Weierstrass said this: tangent x over 2 is the key. Let us make this a letter t, for example. And that's going to be the basis of everything we're going to do. How? So, let's do this. Well, Hmm. What about what is sine x? Well, you could say sine 2 times x over 2. Hmm. you know. So maybe this is all just 2 times sine x over 2 cosine x over 2, right? And maybe we can multiply both the numerator and the denominator by some factor. I don't know, secant squared x over 2. Maybe, perhaps. Yeah, that's what we're going to do. So cosine times secant, by the way, multiplied by secant x. Since secant is just the inverse or the 1 over cosine x, the reciprocal, this is just equal to 1. So cosine times secant is equal to 1. But there's two of this, so we should be multiplying to sine. Sine times secant. Secant is 1 over cosine, so this is should be tangent. Okay? So this we get 2 tangent x over 2. This the cosine and multiplied by the secant will just become 1, so that is ignored. Over secant squared x over 2. We know that secant squared theta is equals to 1 plus tangent squared theta. So this should be 1 plus tangent squared x over 2. Let's substitute t here. We get 2t over 1 plus t squared. And that's the first step of the Weierstrass substitution. Let's move to the next one, which is the cosine. We know cosine x is going to be cosine squared x over 2, double angle identity. So that's what we're doing. And then sine squared x over 2, correct? Multiply both the numerator and the denominator by, again, secant squared theta. All right? Okay, so the top becomes 1. Sine squared theta x over 2, not theta, x over 2, sorry. X over 2, secant squared x over 2. Sine times secant is just tangent, so it becomes tangent squared x over 2 over secant squared theta x over 2 is 1 plus tangent squared x over 2. Substituting the tan x over 2 equals t, we get 1 minus t squared over 1 plus t squared. Uh, let's go back to the original one. So, tangent x over 2 is equals to t. That means x over 2 is equals to arctangent t. Or x is equals to 2 arctan of t. Put the derivative of both sides will become dx is equals to d2 over 1 plus t squared. So let us reiterate again the facts here that we've collected. We now know sine is sine x is equals to 2t over 1 plus t squared. Cosine x is equals to 1 minus t squared over 1 plus t squared. And dx is equals to 2 over 1 plus t squared. Again, t is tangent x over 2. And we're going to be using this to substitute some hard integrals later. So hopefully we remember that. Mm, hold on. Okay, so we will use this in order to solve some stuff. So let's go on with the 59th problem. Question, 58th problem, sorry. I got confused. Uh, God. Question number 58. The integral of 1 over 3 plus cosine x dx. Now, it's kind of difficult to do this with just, identities and stuff. So let's use Weierstrass's technique. So we first let t is equals to tangent x over 2. All right. That's the first step. Second step is to just replace everything with this. So 1 over 3 plus cosine is 1 minus t squared over 1 plus t squared. Multiply that by the dx, which is now 2 over 1 plus t squared. All right. Then, whoop, parentheses everywhere. So the top becomes 2, the bottom becomes, well, I'll just multiply this by this. So 1 plus t squared times 3, that's 3 plus 3t squared. And then the 1 minus t squared over 1 plus t squared, we cancel this and that out. We get plus 1 minus t squared dt. Ah, I should write dt and here. Forgot? Sorry. We get integral of 2 over 4 plus 2t squared dt. So we multiply both the numerator and denominator by 1/2, we get 1 over 2 plus t squared dt. So what's the next course of action here? Well, we can also wait a minute. This looks like an arctan situation, doesn't it? So let's try making it an arctan situation. Uh, let's multiply the numerator and the denominator by 1/2. We get uh 1/2 multiplied by 1 over 1 plus t squared over 2, right? So let us t squared over 2 is also t over square root of 2. So let t is over square root of 2 be equal to some other letter u. Uh, 1 over square root of 2 dt is equals to du. So we need to procure some of that 1 over square root of 2 here. Well, we don't have it, so we can just multiply both sides by square root of 2. Maybe maybe that would be easier. Integral of 1/2 times 1 over 1 plus this becomes, well, u squared. Since t over square root of 2, its square is t squared over 2, which is what we have earlier. Then we multiply that by du, or square root of 2 du. We get square root of 2 over 2. This is now arctangent of u, which is square root of 2 over 2 arctangent of t over square root of 2, which is square root of 2 over 2 arctangent of 1 over square root of 2 tangent x over 2. Crazy. Plus c. So that's crazy, but that's the answer. Next. 59. 1 over 1 plus sine x plus cosine x dx. So we just use Weierstrass substitution for this one. So again, sine x is equals to 2t over 1 plus t squared. Cosine x is equals to 1 minus t squared over 1 plus t squared. Dx is equals to 2 over 1 plus t squared. And that's the 3 that we need. Again, t is tangent x over 2. All right. So we have sine and cosine here. So we can use 1 over 1 plus sine is 2t over 1 plus t squared. Cosine is plus 1 minus t squared over 1 plus t squared. Multiplied by the dx, which is now 2 over 1 plus t squared, dt here, and dt here. Yeah, there we go. So 2 will be stay on the top, and 1 plus t squared will be multiplied across here. So we get 1 times 1 plus t squared is 1 plus t squared, plus this and that will cancel, so 2t. This and that will cancel, so plus 1 minus t squared. T squared and t squared cancel. We get the square root of 2 over 1 plus 1 is 2 plus 2t. We can multiply both the numerator and denominator by 1/2. We get the integral of 1 over 1 plus t. All right. So what's the next? Well, this is just ln of 1 plus t, which is ln of, again, t is tangent, x over 2 plus c. There we go. And question number 60, the last one for the Weierstrass problem. Sine squared x over 1 plus cosine x quantity squared dx. All right. So let's again use Weierstrass for this. If you can find it algebraically and using trigonometric identities, you can do that, but I will use Weierstrass substitution. So sine is 2t over 1 plus t squared. That will be squared. Over 1 plus cosine will be 1 minus t squared over 1 plus t squared. All of that is squared. D multiplied by, of course, why do I forget? 2 over 1 plus t squared dt. So, what is next? Well, let's evaluate the bottom one. So we get 1 plus t squared plus 1 minus t squared over 1 plus t squared. So t squared cancel. 1 plus 1 is become 2 over 1 plus t squared. Again, 1 plus 1 is equals to 2. That is something we should be knowing. If you don't know, just Google it. I don't know. So 2t squared, no, not 2t squared. 2t over 1 plus t squared, all that squared, all over 2 over 1 plus t squared, all that squared, multiplied by 2 over 1 plus t squared. 2, 1 plus t squared, 2, 1 plus t squared, something similar. This t is just getting in the way. So why not move it outside? So by moving outside, we multiply this by t squared because it was inside something squared. So we just move it outside. It's also squared. So that makes sense. I hope that makes sense. And then next we get 2 over 1 plus t squared, 2 over 1 plus t squared. We can cancel that out in order, we get 2t squared over 1 plus t squared. Again, 2 is just factor, so let's just put it outside. So uh how do we do this? Let me introduce to you a technique in mathematics known as adding 1, then immediately subtracting 1. Everybody knows 1 plus 1 minus 1 is 0. I know 0 is 1 minus 1. That's a quote from somewhere else. But basically what we do is we just add 1 when then we divide 1. This is a magic technique known as adding 0. So we get the integral of, I'll rearrange 1 plus t squared over 1 plus t squared minus 1 over 1 plus t squared dt. Okay, so this just cancels out in order to become 1. So the answer is 2t minus, this is just, 2 times arctangent of t. All right. So t is tangent x over 2, so we get 2 tangent x over 2 minus 2 arctangent of tangent x over 2. Arctangent, tangent cancel each other out because they're function in inverses, so they just delete themselves. 2 tangent x over 2 minus 2 and x cancel each other out. So 2 and the 2 here cancel each other out, so this becomes minus x plus c is the answer. There you go. You can even check that out. That's true. All right. I believe that does it for the Weierstrass and the Trig sub. So I'll see you in the next question, which should be happening in a few seconds. Moving on with definite integrals. Now, we know that the integral is representative of the area, right? So this is representative of the area. So if we want to find the area from, say, A to B, we need to find the values of the area function from A to B. How do we find the area, right? So let's try visualizing it using a graph. Here, this is from A and then B. All right. First, we need to find the area from 0 to B, which can be expressed as big A of B. And then we subtract by the area from 0 to A. So all that's left is the area from between A and B. All right. And this is the uh, uh, formula for the area of the graph there. Assuming that we know, of course, the area function. So we will be using that in order to answer these definite integral questions. Number 61. The integral of 1 plus x cubed dx as x goes from 1 to 4. Well, first we find the integral of this, which is the antiderivative, or that's the same thing. So the integral of 1 is just x. The integral of x cubed is x to the 4 over 4. And now we try to find its values from 1 to 4, the area. So what we can do is to insert 4 here first. So substitute 4 into everything. So 4 plus 4 to the 4 over 4. And then we subtract by, let's put parentheses in it so it's easier to visualize. And then minus the substituting 1 into everything. So 1 plus 1 to the 4 over 4. So evaluate both sides. So this becomes 4 to the 4 over 4. Well, one of the 4s will cancel out. So this becomes 4 to the 3, which is 64. This entire thing is 68. Minus. This is 1 plus 1 over 4. 1 to the 4 is just 1, so there's nothing hard about that. So this is 1 plus 1 over 4, which is 5 over 68 times 4 is, let me just calculate it here, 272. So it's going to be 272 minus 5 over 4, which is going to be 267 over 4. And that's the answer. 62. The integral of sine x dx from 0 to pi over 2. Let's find the antiderivative. This is going to be negative cosine x. And then we're trying to find its values from 0 to pi over 2. So pi over 2. So cosine pi over 2 is 0. Then we subtract by, and then cosine of 0 is negative 1. So it's going to be, no. Cosine of 0 is positive 1, but it's negative, so it's going to be negative 1. Alright? And since negative negative is positive, the area is going to be 1. Question number 63. The integral of 1 over 1 plus x squared dx as x goes from 0 to 1. So this we know is just arctangent of x, and then 0, 1 here. So this is going to be arctangent of 1 minus arctangent of 0. Now, in order to find arctangent of 1, we have to remember tangent of what angle is equals to 1. In other words, sine of what angle over cosine of what angle is equals to 1. So, in other words, what angle would sine and cosine have an equal value? So, sine of what angle equals cosine of what angle? Pi over 4. Of course, pi over 4. Because sine pi over 4 is root 2 over 2, and cosine pi over 4 is also root 2 over 2. So, this is going to be pi over 4. And some of you may be asking, well, what about pi over 4 plus 2 pi or 2 pi k, where k is uh, an integer? Well, we have to consider the the domain of arctan. The domain of arctan and arctangent x is actually from negative pi over 2 to pi over 2. Uh, no, the range actually. Range. Sorry, not the domain. The range is equals to exclusive negative pi over 2, pi over 2. So it cannot exceed that or it cannot be lower than that. So pi over 4 is correct. And as for arctan 0, well, arctan 0, tangent of what angle is going to be 0? In other words, sine of what angle over cosine of what angle is 0? If it's 0 here, this becomes 0, this becomes 1. 0 over 1 is 0. So minus 0, you get pi over 4. That is the answer. 64. The area from the integral of square root of 4 minus x squared dx as x goes from negative 2 to 2. Now, before we use some trig sub or anything, let's think about what this shape is. This is basically the equation y is equals to square root of 4 minus x squared. If you can graph that, maybe we can have some insights into what the function is. Let's square both sides. Y squared is equals to 4 minus x squared. Let's put x squared on the other side. X squared plus y squared is equals to 4. This is familiar because this is the area of a circle. So if you, the equation of a circle. So this has the form x squared plus y squared equals some r squared. So this is going to have to be like a circle. Let me just draw a circle like that. And the radius is the square root of 4, which is equal to 2. So this is basically x squared plus y squared equals 4. But what about y equals square root of 4 minus x squared? Well, 4 minus square root of x squared, its range can only be from 0 to 2, positive 2, exclusive. Because, well, this cannot be negative since there's no negative on the outside. And please don't say it's square root of something is positive or negative something. That's not how it works. This is just positive. So it could be 0 and it could be all the way to 2, the range. Yeah, the range from is 0 to 2. And anything beyond 2, it would be imaginary, which we don't really care about. So so this actually, this portion is actually y is equals to the square root of 4 minus x squared. The bottom one is its other companion, negative square root of 4 minus x squared. And then why did it form a circle when it's only a half circle? Because in reality, this is y equals square root of 4 minus x squared. Why did it form a circle? Well, when we squared it, we actually included the negative version in it because as you know, if you square root both sides of this equation, you have to put plus or minus on the outside of the square root to guarantee that you get all the values of y. But again, square root of something like 9 is not equal to plus or minus 3. It's only equal to 3. All right. It's the square rooting both sides of the make it actually uh, a plus and minus. All right. So with that out of the way, we do know that the the shape that we are finding is a semicircle with radius 2. So this is on 2, x equals 2, and this should be on x equals negative 2, since the distance from the origin is 2. So from negative 2 to 2 is just the area of this circle. Semicircle, sorry. So what is the area of a circle? Well, it's pi r squared, and then 1/2 since this is just a half circle. So r is 2. So 1/2 pi times 2 squared. 2 squared is just 4. 4 times 1/2 is 2 times pi, and that is the answer. 2 pi. Question number 65. the integral from square root of 4 minus x squared, sounds familiar, but from -1 to 1. What does this look like now? Well, it's just the half circle, something like that. But instead of from this edge to this edge, it's actually from this edge to this edge, not to scale. So -1 to 1. It's symmetric along the y-axis, so we can just focus on one and maybe we can double it. So why not that? We will learn that later, but just know that this is symmetric. Okay? So how can we do this? Well, this is just three shapes basically. It's this one, but multiplied by two, since this and that should be the same. And then we add this, the overarching thing. This, yes. And that would be our answer, the area. So how do we go about finding the solution for that? Well, what is the formula of a triangle? Let's go with the triangle first. It's just pH over 2. And then we have to multiply that by 2 since there are two of them. So let's focus on the triangle first. The distance from here to here should be 1 since that is the uh, bounds. This is the origin and this is the bound where it ends, right? So what else? Hmm. Well, this should be 2 because the radius of the circle is 2. So what should this be? By Pythagorean theorem, this is the square root of 2 squared minus 1 or the square root of 3. And 1 square root of 3 and 2, that is the popular 30, 60, 90 triangle that is always in trigonometry and stuff like that. Since this is opposite to the longer edge, this is angle pi over 3 or 60 degrees. Right? And it looks like 60 degrees, so it checks out. So, with that out of the way, we can find the area of this triangle, which is going to be BH over 2 again, which is a square root of 3 times 1 over 2, or square root of 3 over 2. That's the area of one triangle. And then we multiply that by 2 in order to get two triangles, right? So it's just a square root of 3. This is square root of 3. How about the arc? Well, let me erase this. Although I will redraw this, so there's important information there. Again with the triangle, let's see. Here, we had two triangles earlier. This one had an angle of pi over 3 since it was facing square root of 3, the square root of 3 aside. So this should be pi over 3. This is also pi over 3 by symmetry. So this should be pi minus 2 times pi over 3. Since pi is 180 degrees, all right? So this is 60 degrees, so we should be able to just find whatever this is. Uh, that should be, hold on. Okay, so 2 pi over 3, pi minus 2 pi over 3, this is going to be pi over 3. So the angle for this one is also pi over 3. So that's good. What is the area of a circle? Well, the area of a circle is pi r squared. The area of a segment of a circle or an arc or something like a slice of pizza should be, well, the theta over 2. Since a full circle is 2 pi theta, 2 pi in angle, and the formula says it's pi r squared, so it should be the angle over 2. Then multiplied by r squared. We know r squared already, that's going to be 2 squared. Theta is pi over 3. Then multiply by 1 half since, well, there's 1 half here. And let's evaluate this thing. So what is this? Well, this is going to be 4, and 4 times 1/2 is 2, and pi over 3 is pi over 3. So we multiply those together, we get 2 pi over 3. All right? And then we just add these two together, and if you know how to calculate that, that is the answer. Square root of 3 plus 2 pi square root of 3. You can calculate that if you want, but I'm gonna leave it at that. Question number 66. And now we enter the class of problems that involve infinity, so-called improper integrals. So here we have ln x over x dx as x ranges from 1 to 2. Of course, you can do substitution here. Let ln x is equals to 1 over x. And then, no, not 1 over x, sorry. I'm confused. U. So derivative of ln x is 1 over x dx is equals to du. So all that. But when we substitute things, we have the ability to uh, change the bounds. So, and we do have to change the bounds. So in this example, the lower bound is at x is equals to 1. Let's find the value of u. It's going to be 0. And if x is equals to 2, u has to be, well, ln 2. Again, we refer to here in order to find the values here and here. So don't be confused. We get ln 2 and 0 of, well, u du. This is u squared over 2 ln 2 0. Ln 2 squared is just ln squared 2. I can actually do that. Over 2 minus 0. So just 0. So the answer is this. Okay, that's the answer. You can also evaluate that if you want. Next. Question number 67. Actually, so remember earlier when I said improper integrals? Well, this is the actual improper integral. I was confused earlier. So this is an improper integral. You'll see in a moment. So from negative 2 to 1 or 1 over x squared dx. So maybe you just learned about antiderivatives and you can use your knowledge of antiderivatives. This is just negative 1 over x. Right? Because this is x to the negative 2. So integral of that is x to the negative 2 plus 1 over negative 2 plus 1. Or negative 1, then x to the negative 1. Or negative 1 over x. So you said I won't put plus c because this is just a definite integral, and that's correct. And then you substitute negative 2 and 1 here. So you did what I told earlier, and then maybe look at negative 1 over 1 and minus, and then negative 1 over negative 2. Negative, 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 that's negative 1/2. And then minus 1, that maybe your answer is negative 3 over 2. This is wrong. Let me just say, this is wrong. Let me just put the word wrong here in order to encapsulate how wrong it is. Why? Let me tell you. If you remember the graph of y equals 1 over x squared, you will remember that it looks like this. Something like that. And this is actually going to infinity. So, and it's all positive. It's all in the positive x-axis. So why is there negative area? By the way, negative area is just area below the x-axis. Is the area here below the x-axis? No. We just got negative area out of doing whatever that was. So, no, we cannot take the area by just doing whatever that was. Because look, this both go to infinity. So maybe the area is infinite and we just misinterpreted it. And that indeed is what we did. So what do we do here? Well, we do have to split the integral into two parts. from -2 to 0, and then from 0 to 1. So we can avoid the discontinuity that is going on here. But we cannot evaluate the area as it goes to 0, because that's what do you call it? Undefined. All right. So what we're going to do is actually to evaluate the limit as, let's say, some value a goes to 0 of the integral from -2 to a of 1 over x squared dx. And then we add the area of this one, in this part. So again, let's put the limit as a goes to 0 of the integral uh, a to 1. 1 over x squared dx. You have to specify the direction. So this has to be 0 minus, since it's going from -2 to 0. So it comes from the negative side, so it's 0 minus. And then this should be 0 plus, since it is going from 0 to 1 on the positive side. So 0 plus. So let's try to find the answer here. This again is just -1 over x. That is indeed uh, the antiderivative. That's not wrong. And then we have to find the values a and the -2. And then don't forget the limit. And we add by the limit again. Okay. And then the antiderivative -1 over x. And then as this goes from a to 1. So this is, let's evaluate it. This is going to be -1 over a minus -1 over -2. All right. Again, the limit here, a goes to 0 minus. All right. Plus the limit as a goes to 0 plus here, the -1 over x, and then 1, then no, sorry. 1 over the top first, 1 minus -1 over a. All right. So 0 minus, let's bring back the graph for 1 over x. 1 over x is usually this, but since it's -1 over x, it goes like this. This is y equals -1 over x. All right. So, going to the negative 0, yeah, the 0 negative is going to positive infinity. So this is going to negative, then positive infinity. No, 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 no. No, just positive infinity. Since I'm actually talking about -1 over a. So it's actually just positive infinity, sorry. Uh, minus 1/2. I don't know what minus 1/2 would do, but it's there. So plus -1, so it actually should be -1. And then this is negative negative, so it's positive. And then 1 over a is this. Again, it's the normal y equals 1 over x. And 0 plus, it actually goes to positive infinity as well. The infinity is here, the infinity is there. It's infinity everywhere. So the area is actually divergent. So it's not negative, it's actually divergent and it's positive. So this teaches us that we do have to be careful about certain integrals, because it's not just plug and chug, it is just the careful observation. Again, if the area should be positive, but the area that we found is negative, something must be wrong. So that's how you can spot that. Question number 68 is also an improper integral. Uh, the integral of 1 over x plus 1 dx from -1 to 0. So we just find the antiderivative of this, which is ln of x plus 1, and then from 0 to -1. Ln of 0 is undefined. So we cannot put -1 here. We can put -1 plus. Is this just a shorthand for the limit? We should have a limit as a goes to -1, blah, blah, blah. But let's just put -1 plus here so we know what we're working with. So let's just put everything in. So ln of 0 plus 1, and then minus ln of negative 1 plus 1. Now, remember what the plus in the what where the exponent should be represents. Actually represents what? Negative 1 plus is a bit like negative 1 plus 0.00000001. It's a small quantity. It's a small quantity. So it's like 0.9999999. So it's a little bit positive. It's more than negative 1. That's what it represents. So this should be negative ln of 0 plus, or something along those lines. Ln of 1 here. Ln of 1 is just 0. Then minus, and then ln of 0 plus. Now, ln of 0, ln of 0.0000 that is a big negative uh, number, n, big N. Because ln of e is 1, and then anything less is negative. Actually, no. ln of 1 is actually equal to 0. Alright? Anything less is negative, anything greater is positive, right? So this should be a large negative value. And 0 plus is basically getting smaller and smaller and smaller. And it's a limit thing, so this is negative infinity. Negative infinity, you can say it's positive infinity. That is the answer, or divergent. The area is divergent. You don't say the area is positive infinity. You say it's divergent. Okay. Question number 69. The area of 1 over x dx as x goes from 0 to infinity. Now, let's see if there's inconsistencies here. They said from 0 to infinity, somewhere there. So something like that. The area of all of that. So what is the area of all of that? So first, we get the antiderivative, and then we put infinity here and then 0. Since it's going to the positive side, 0 plus, right? Don't forget the 0 plus. Actually, it doesn't matter if it's 0 plus or 0 minus because we put the absolute value here anyway, and that would just, you know, that would just be 0 plus anyway, even if it's 0 minus. But 0 plus is still a good practice. First, we get ln of infinity. This is bad notation, by the way. You should put a limit here, but I'm just winging it. Minus ln of 0 plus. ln of infinity, well, ln, or the natural logarithm, is an increasing function. So it never decreases, it just increases. So as it goes to infinity, this also is infinite. Minus and ln 0 plus, as we established earlier, is going to go to negative infinity. Therefore, it's just infinity. Or the integral is divergent. All right. The area is not infinity. Infinity is not a number; it's a concept. But we do know that it is divergent. It just grows bigger and bigger. All right. Question number 70. The integral from infinity to 0 of sine x dx. Well, this is going to be negative cosine x dx. No, cosine x. So that is the antiderivative. And then it goes from infinity to 0. Now, what is cosine of infinity? First, what is the behavior of cosine? Well, it just goes like this, right? It goes up and down and up and down, and it has nothing. It just goes from 1 to negative 1. It has no goals in life. It doesn't want to be 0. It doesn't want to be infinite. It doesn't diverge to any value. It just goes up and down and up and down forever. So, that doesn't exist. Cosine of infinity, or well, the limit of cosine x as x goes to infinity doesn't exist. So we can say that the area is divergent. It changes from time to time. And what does this mean exactly? What does it mean by a divergent area that doesn't exist? Well, take a look here. The graph for sine should look a little like this. So it goes here, and then 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 here. Pardon the accuracy, but this is like area A, and since this is below the line, this is like negative A area. So this is A and then negative A. So it just switches from positive, negative, positive, negative. As it goes to infinity, it just continues on that switching. So there is no definite area. There is no area per se. It's not even zero. It could be anywhere from zero to whatever A is. So, or negative A for that matter. So the area is divergent because it can't decide for itself. So we just decide it's divergent. Question number 71. The integral from 0 to infinity of 1 over 1 plus x squared dx. This again is just arctangent x and then infinity to 0. Now, arctangent of infinity, what is that? Well, recall the tangent of x, let's graph it. It looks something like, this is the y-axis and like x-axis. It looks like this, right? With the asymptote, or the line that it never touches being x equals pi over 2. Arctangent is a similar case. It just flip a bit. So instead of that, it just goes like that. Again, with the asymptote being y equals pi over 2. It never reaches that, but at the limit, at the limit towards infinity, it goes to pi over 2. So arctan of x as x goes to infinity. This is pi over 2. So we can say pi over 2 here for the infinity thing. Minus arctan of 0 is just 0. The answer is actually pi over 2. That's the end for definite integrals. Now, we will now use definite integrals to solve geometry problems. We have 5 here. First, question number 72. Find the area of the region bounded by y equals x squared and y equals x plus 2. If you're confused here, you can go to Desmos in order to graph both of these, but I will try drawing the graph. It looks something like this. This is y equals x squared, and this is y equals x plus 2. Not to scale, of course. So how do we find the area bounded? What is the area bounded? This is what we're referring to. They're bounded by those things. So it's in between of them, per se. So uh this is should be the what? The x-axis. Let me just draw properly. It's something like that. Oops, I draw too long. So it's something like that. So how do we find the area? Well, if you pay attention, the area, the integral from this side to this side of x plus 2, uh, it's actually this area, right? It's all this area. But in order to find this area, we have to find the area underneath the y equals x squared, and then we subtract it. So we do this. Why? Because the area of this, right? Something like that. The area of this is, well, this. So if we subtract that, we can find the area in between them. So this is going to be our uh, our functional formulas for the area of the pound. What is A and B? That is the question. Well, A and B are the points in which they touch or they intersect. So let's set them equal to each other. Then let's put everything to the other side. And then let's solve this using a method of your choosing. Let's go with the Pythagoras, no, not the, no, the quadratic formula because most of you are familiar with that. It is negative b plus or minus square root of b squared minus 4ac over 2a. So that's the values of x. This is, of course, brought to you by the completing by square method. So b is negative 1. So negative b is just positive 1. Plus or minus square root of b squared should be 1 minus 4 times a, which is 1, times negative 2. All right, over 2 times 1. Rewrite 1 plus minus square root of. This is 1 minus 4 times this hoopla, which is going to be negative 8. Negative 8 is positive 8. So 1 plus 8 is 9 over 2. And square root of 9 is just 3 over 2. 1 plus 3 is 4 over 2. 1 minus 3 is negative 2 over 2. Or 2 and negative 1. These are the values of x that we're trying to find. There should be negative 1 since on the left, and there should be 2 since it's on the right. So we're on the right track. Let me just erase this. All right, so A and B, now we know what A and B are. So we can erase that and then replace it with the actual values. So negative 1 here, 2 here, negative 1 here, 2 here. So let's try finding the areas. So this first. The integral of x squared over 2. The integral of 2x is just 2x. This goes from negative 1 to 2, something like that. Minus the integral of x cubed is going to be x cubed over 3. And then 2 negative 1 here. Let me just put the parentheses on this so we're not confused. 2 squared is going to be 4 over 2 plus 2 times 2, 4. Negative 1 minus negative 1 squared is just 1 over 2 plus 2 times negative 1 minus 2 cubed is 8 over 3 minus negative 1 cubed is just negative 1 over 3. All right. Minus, oh shit, sorry. Oh yeah, that's it. Nothing else. We have nothing else. Okay. Yeah. So that's the uh we just evaluate that and then we can find the area. So let's try calculating it. This is 2 plus 4. This is minus 1 half. Then plus minus, so plus 2 minus 8 over 3 minus 1/3. So negative 8 over 3 minus 1/3, this is negative 9 over 3 or negative 3. Uh, sorry. Ah. Negative 1 half here, 6, and then plus 2. So evaluating that, we get 6 plus 2, 8 minus 3 is 5 minus 1 half. Is equals to 9 over 2. And that's the answer. So, yeah. Let's get my switches out. Question number 73. Find the area of, oh, not the integral. Area of region bounded by y is equals to x squared minus 2x and y is equals to x cubed over 9. In these times, it's really hard to visualize it, so you can just do mathematics in, but let's try to visualize it because visualization is always good. So y equals x squared minus 2x should look like that. It's just a parabola. X cubed over 9 is just an x cubed thing. There's no other extra terms. So maybe it looks like that. I don't know. but we don't know what it actually looks like. So we have to find the intersection points. So where do these points intersect? Well, let's just equate both of them together. X cubed over 9 is equals to x squared minus 2x. Then just multiply 9 to both sides. X cubed equals 9x squared minus 18x. Yeah. Put everything to one side. X cubed minus 9x squared plus 18x is equals to 0. And then factorize x, and then x squared minus 9x plus 18 equals 0. This is, well, let's see. X here, and then maybe 3 and 6. So this will be 6x and then 3x. All right, this is the, yeah, that's the method. But it's negative, so this both has to be negative. A negative, negative, positive, so it checks out. X minus 3, x times x minus 3, x minus 6, that is equal to 0. X is now equal to 0, 3, 6. So they have three meeting points. And what does this mean? Well, it means that there are certain points at 0, 0, 3, and 6, somewhere high up. Maybe they meet like that. Then something like that. Not really, not really accurate since it curves, but it looks like that. So there are two intersection points. Let me just display it easy more accurately. This is hard to visualize. Something like that, and then the area is something yeah, like that. So we have 2 points. This is 0. Uh, this is 3, and this is 6. So how do we find the areas of this? Well, we have to know what is the bigger one here. After all, it could be any configuration other than this, but this looks like the most likely since it passes to all 3 points, and x cubed kind of looks like that. So let's build a table from uh, the function and then the value x. So 0, 3, 6. The values are 0. All right, that is given. And then for the middle, what happens? Well, what about let's say 1. So for going here, it's 1 times 1 minus 3 and then 1 minus 6. Positive, negative, negative is positive here. So y equals x cubed up over 9 is greater than uh, x squared minus 2x if it's positive. All right, because looking back at the original equation, it's actually x cubed minus x squared minus 2x or whatever. So it means it is greater than that. Since we subtracted it, it being positive makes it greater. So in the middle of 3 and 6, maybe 4. So 4 and then 4 minus 3, 4 minus 6. Two positives and a negative, it's a negative. So this means x cubed over 9 is less than x squared minus 2x. And then after that, it's just going to be greater, but we don't care about that. So yeah, that is the that's the easy part. The hard part is to set up all of this again. Again, we just look at the graph. We just look at the graph. So we know that x cubed over 9 is greater in the first one. So let's set that up. 0, 3, and then x cubed over 9, since it's the one bigger, minus x squared minus 2x, since it's the one smaller in this case. Then we add the second set, which is x squared minus 2x is greater, so it's going to go first. From 3 to 6, x squared minus 2x. And then We subtract by from 3 to 6, x cubed over 9, so it is lesser. So we just solve for all of these. The top one is x to the 4 over 36, and then 30 here, minus, and then this is x cubed over 3 minus x squared, 3 and 0. Uh, so that's going to be the first one. And then the second one is like the earlier ones, but from 3 to 6. Let me just put down here. Minus, this one is x4 over 36 again, but from 3 to 6. Erase this one. And we need to evaluate all of this. So evaluate all this, just put some algebra stuff in there. But if this is correct, the answer should be 5 over 2. And that is the real t. All right. So 5 over 2 is the answer. That means that is the area of the regions bounded by both of those equations. So there's two regions and their combined area is 5 over 2. If you just want to find the area of one region or the difference or whatever, you can do other stuff. But the area of the regions, let me just, I should put an S in here. The area of the regions bounded by this is 5 over 2. Right. Again, you can calculate it. You're free to calculate it if you want, or maybe use your calculator. So I don't have one here. 74. What is the volume of the solid generated by rotating y is equals to square root of x squared plus 2 along the x-axis from 0 to 1. What does this mean? Well, let's graph the original equation first. Maybe something like this, since square root of x tends to be like that. So from 0 to 1 is from maybe 0, I don't know, it should be here, maybe. 1 is maybe here. So what this says is actually mirror the image along the x-axis and rotate it like so. Let me just, so something like, let me just extend this one. Something like this is what we're trying to find. All right. This entire solid. This is the solid of revolution. It revolves. Revolution. It revolves around the x-axis. All right. So something like that. We revolve apart along the x-axis, and then we're trying to find the area or the volume of the shape that is formed. How do we go about even doing that? Well, we're going to be using something called the washer method for this one. And let's derive the washer method. What is the washer method? And then how do we use it? So in order to find it, we need to put, we need to take a little strip, a bar, all right? And then we rotate only that along the x-axis, right? We just focus on this little a disk here. This is why it's sometimes also called the disk method. Washers look like that, I think. So the disk here is actually a very thin cylinder, a squished cylinder. And the area, the volume of a cylinder is just pi r squared h. So we just need to find what R and H is. Basically, if you think about it, this is the H and this is the R, right? What is the R? Well, looking from the original function, the R is f of x. So R is just f of x squared. Multiply pi here. And then the H is, what is the H? Well, this a little bit. It's something that gets smaller and smaller. Let's represent that with dx. And again, dx goes to 0. Much like a Riemann summation and whatnot, this goes to 0 and the amount of this go to infinity. So there. So pi fx squared times dx. Let me just write that clearly. So that is the volume of a disk. The entire thing, what is the volume of that? It's just the integral. So the volume of the entire thing, let me put it here. The volume of the entire thing is just from a to b, pi, and then f of x squared dx. And if you can solve that, that's good. You found the volume of the solid of revolution, and that's nice. So let's try finding it. What is the volume using this formula that we just gathered? Well, the function is x squared plus 2. Again, this is y equals f of x. That's the style that we're going for here. And the f of x is x squared of x squared plus 2. So we get the integral from a and b. A and b is 0 to 1, as I said here. And then pi times f of x squared. So square root of x squared plus 2. That is squared dx. The square and the square root cancel each other out, so pi can go outside for a bit, then 1, 0, then x squared plus 2. X squared, the antiderivative of x squared, as well known, is x cubed over 3, and then the antiderivative of 2 is just 2x. So x cubed over 3 plus 2x. And we multiply pi on the outside so we don't get confused, and then 1 and 0 here. Let's evaluate. Pi times 1/3 plus 2. And then subtract by pi times 0 plus 0. So this is 0, so nothing. 1/3 plus 2 is 7 over 3. So the volume is 7 over 3 pi cubic units. That's the volume. Number 74. Number 75. Same as 74, but along the y-axis. So we still have the same graph as the question says, but and then the same bounds. But one main difference is that we're rotating along the the y-axis, so it should look like this. For example, maybe let's try a different curve. Let's just pretend this curve is our actual curve, but it's not. But from 0 to 1, we're now going up around like this. And like that. And then mirroring everything. So something like okay, something like that. And then maybe something, yeah, like that. So well, how about if it's like from A to B, from some normal A and B? Maybe from here to here. Well, it should look like that. There's a hole in the middle, right? There's a hole in the middle, and that's fine. This is like a donut, you know? So what is the volume of this? It's different because we can't use the washer method earlier, and maybe it's like dy, but we only have the x y equals f of x to go off of. If we can transform that, but I'll leave that to you. But I'm going to introduce something else called the shell method. Again, the trick is to get some strip, uh, yeah, so, like a random strip here, and then you rotate only that along the curve. So, for example, maybe this one, and then this gets rotated like that, and then this gets rotated like that, and then the resulting shape is something like that. It's like a tissue roll paper, for in the bathroom. I don't use them. I use soap. Anyway, uh, this is a tissue roll paper. So it's basically just a cylinder minus another cylinder. Or, if you think about it, is this rectangle then rotated, right? So that's the definition. Maybe the volume, we can express that as the area of the cross section, which is the rectangle strip, multiplied by the circumference of it, the mean circumference. So, like the average circumference of the thing. So, we can find these both. The circumference here is, well, let's define some lengths here for now. So the height is f of x. The width is a dx. Here the cross section should be f of x dx. All right, dx again goes to 0. All right, the circumference, what is it? Well, from here to here, the radius of the small circle is x. All right, and then the radius of the big circle is x plus dx. So the mean circumference is the average of both of these. So x plus dx over 2. Then we multiply that by 2 pi, right? In both of these cases, dx goes to 0. So we can ignore this dx since it's multiplicative. And this dx goes to 0. Yeah, it's additive, so it doesn't do much. It just goes to 0. This is x plus x over 2, which is 2x over 2, which is x, times 2 pi. Then f of x at dx. Let's write it here. The volume of a tissue roll. So next time you're in the bathroom, wondering what you could do, you can find the volume of the tissue paper by doing this. So it's actually 2 pi, the constants, times x times f of x dx. That's just one tissue paper. How about the entire shape? The area is yeah, you just, put the integral here from a to b. 2 pi can go outside since it is constant, just a constant. So you just multiply it by x and then f of x. That is the shell method. So again, the washer method, you just square the input, but in the shell method, you have to multiply it by x. So let's use it here after I erase this entire thing. So again, let me just put the formula there so you can see it. So the volume of the entire thing is going to 2 pi times times the integral from 0 to 1, x times the square root of x squared plus 2 dx. We can do integration by substitution here. We can say let x squared plus 2. Let's do something different. Let's square root of x squared plus 2 plus u. This means x squared plus 2 is u squared. 2x dx is equals to 2u du. So we have an x here and the dx here. We can transform that into u du. We can divide both sides by 2, so we get x dx equals u du. So we also need to replace the bounds. So from x equals 0, this becomes u equals square root of 2. If we put 0 here, it's just square root of 2. X equals 1, u becomes square root of 3. So from the square root of 2 to the square root of 3, uh, okay, sorry. This becomes u, then u du. Again, this becomes u, then this is going to be u du. Gets? Then 2 pi outside, so don't forget about that. 2 pi, and then the integral from square root of 3 over square root and square root of and whatever. So u squared du. This is u cubed over 3. Square root of 3, square root of 2 times 2 pi. Square root of 3 cubed is going to be 3 root 3 over 3. That and that cancel each other out. Minus square root of 3, square root of 2 is 2 square root of 2 over 3. Multiply by 2 pi, we get 2 square root of 3 minus 4 square root of 2 over 3, all multiplied by pi. That is the volume. All right. One more. 76. Find the volume of the solid generated by rotating the, re the region described in question 72 along x-axis. What is the region for described in 72? Well, it's this one. No, no, this one. So it's this one. It's this region. So we have to rotate that one along the x-axis. So how do we do that? Let's try visualizing it. Again, it's good to visualize stuff. So it looks like that. All right. And then rotating it. Again, the trick here is to mirror the image. That looks mirrored. It's mirrored, and then maybe that. Mirror the image so it looks mirrored. It doesn't look mirrored. Whatever. Let's just fix that for a bit. uh, I'm struggling to draw here. This, that. All right, and then draw some funky looking circles here so it looks round enough. So we're trying to find rotating the area of this one. So it looks like maybe like that, and then that, that. This thing is what we're trying to rotate here. It's hard to visualize, no? So like we did earlier, let's try just finding some easier uh how to find the volume of this. Well, the full volume is bigger than the volume that we want. All right, so the full volume, which is just the one that x over 2 is describing, x plus 2 is describing. So that's the bigger volume. Then we subtract by something to get the result volume. We just subtract by this. We don't want this, so we subtract by this, which is the volume that is generated by below the y equals x squared. Yeah. equals the volume that we're looking for. So let's try finding in the big volume first. So big. Let's represent that with a big. All right. So what's the big volume? Well, washer method. This it can be used the washer method. So it's just x plus two and then squared dx from what points, right? Earlier we found that the points are from -1 to 2. So uh maybe there's a solution. You know. So let's try finding the area now. So big and small later. So expand this, we get x squared plus 4x plus 4. That is we find the integral from -1 to 2. And then integrating it, we get x cubed over 3 plus 2x squared plus 4x from -1 to 2. All right. Evaluate this. You should get 21 pi. Uh, I'm already running out of time here. So 21 pi is the big one. And then we subtract that by the small, uh, by the smaller volume. Let's say this is small. So this is the integral from -1 to 2 of x squared x. This is x to the 4. Integral of x to the 4 is x to the 5 over 5 from -1 to 2. Again, I forgot the pi here. Actually, I forgot the pi earlier, but it should have a pi. So this becomes 2 to the 5 is 30, 2 over 5 minus -1 over 5, 33 over 5 pi. This is what we want to find. So let's evaluate 21 pi minus 33 over 5. So minus 33 over 5 and then multiply by 5. We just factored pi out of the equation. So 21 is 105 over 5 minus 33 over 5 pi. This is equal to 72 over 5 pi. And this is the answer. This is the volume of the solid generated by rotating the region as described in question 72 along the x-axis. 72 over 5 pi. Right. That's it for now. We just learned about the definite integrals and then geometry problems. Next will be the definite integral properties. So I'll see you in the next part. Let us proceed to the next question. For this part, we're going to talk about definite integral properties, starting with the first one. The integral of f of x dx going from -a to a. Uh, suppose that mm, the integral of from a to 0 f of x dx from 0 to a, sorry, is equal to some value a. Yes. So if the first one says if uh what is the integral again if a f of negative x is equals to negative f of x. Now, how do you go about doing this? Well, remember the range here, the domain, sorry, of our what we have to calculate. We go from -a to a, and there's 0 in the middle of it. So let's divide it into two parts, from -a to 0, and then from 0 to a. So that's two integrals. From from -a to 0, f of x dx plus from 0 to a f of x dx. Now this by definition is just a. All right. This, let's try to calculate it by substituting it first. Let me just fix it up. Yeah. By substituting x to be negative u. So we can switch up the order later. So if this means dx is equals to d. If x is equals to 0, u is also equal to 0. If x equals negative a, then u should be equal to a, right? So the bounce is now from 0, from a to 0, which is reverse, I guess, f of negative u, then this multiplied by, this should be negative u, so negative. Now, a good uh, a good integral property is that if you have a negative here, we can use that to flip the integral bounds to get. So we get the negative gets cancelled out in favor of flipping the integral bounds. And f of negative u is going to be negative f of x. All right? This is just negative a. So this this is actually the f of u here. F of u. Ah. So u and x, it doesn't matter what letter you use. If it's the same bounds and then the same function, and then you can just replace the u with an x. And it's going to be fine since u is just dummy variable, so it doesn't matter what letter it is. So just is negative a plus a, this is equal to 0. So if f of negative x is equals to negative f of x, and then you're given the integral from negative a to a, the answer will be 0. All right? The second part of this is what if f of x, negative x, is equals to f of x. This would be the second part. So again, we're given the integral of this. So let's divide it into two parts again. From negative a to 0, f of x dx, and from uh 0 to a, f of x dx. Again, this is just a, as we previously discussed. And what about this one? Well, let's do the same thing earlier. So let x equals negative u, dx equals negative du. So the bounds become 0 and then a, like earlier, f of negative uh, u du, times negative du. So the negative here, we can flip the bounds together. So we get a to 0 and then du. Then f of negative u is just f of u. And this is just this. It's just the definition of this earlier, right? You say, well, the letter is different. Again, it doesn't matter because, well, we're basing it off like similar placements of the variables and whatnot. The substitution, it doesn't really matter if it's like x or u or z or whatever. Uh, it represents the same function and graph. So this is also a. We could also say u is a dummy variable, meaning it's just a puppet, maybe, because x here is the main one, and we replace it to u, and it turns out that we have something similar to x. So u is just a dummy variable. It could be any other variable. So that's what I want to let you know. So this is actually a plus a. This becomes 2a, and a is this. So let us summarize what we got. The integral of negative a to a f of x dx. Okay? If f of negative x is equals to negative f of x, then the integral is equal to 0. No matter what the integral is, if it's if it can be of the form f of negative x equals negative f of x, and then the integral is just 0. if let me put it down. If f of negative x is equals to f of x, then this is going to be 2, then the integral from 0 to a f of x dx. How can we visualize this? Well, you can think of the first case as like this. So the first one it may be positive, the second one is a negative, just a negative version. So we're trying to find the area from negative a to a. This is just the negative version of this. So they just cancel each other out, you know? And for the other one, maybe the it's like that. And then we're trying to find the area here. From negative a to a. Since they're the same thing, f of negative x is just f of x. So this is double of whatever this one is, right? So that's the logic behind it. The top one we call the odd function property because functions of this nature are odd functions. And then the second one is the even function property. And they will be useful for evaluating seemingly hard integrals. So let's evaluate the next few questions using this trick. The integral from negative 100 to 100 x cubed cosine x dx. So immediately when I see negative something to positive something, I immediately think of the odd even properties. Maybe there's something hidden in that. You can use the integration by parts here in order to answer this, but I'm just going to mm, I'm just going to see if it's even or odd first, so it's easier to answer it later. So x cubed is it x cubed cosine x, is this even or odd? Well, what we can do actually is to look at each components. Uh, much like in uh positive and negative, right? So two positives like make a positive, two negatives make a positive, and then a positive and negative is just a negative. So the amount of positives and negatives make it a positive or negative. So if there's an odd number of negatives, the thing is going to be a negative. So like negative one times negative one times negative one. There's an odd number of negatives, so the answer is negative one. So let's try if these are how many odd functions there are. X cubed. This is f of x. Let's try calculating for f of negative x. This is going to be negative x and then cube. So, you know, negative x cubed is just negative x cubed. So it's negative of the original. So the first one is odd. Cosine of x. What about cosine of x? F of negative x. Is cosine of x odd or even? Well, let's see. Uh let's try some values. Maybe we can find it that way. So we f of negative pi over 4 is equal to no positive pi over 4. So it's root 2 over 2, all right? And then f of negative pi over 4 is also root 2 over 2. Is that true? Maybe. No, no, it is true. So this is actually an even function. Cosine is famously an even function. So this should be even. You can check it in Desmos if you have to. It's symmetric along the x-axis, y-axis, sorry. So the graph of cosine looks like this. Yeah. So it's symmetric. So it's even. So this is a odd times even. So this should be an odd function because there is an odd number of odd functions, and therefore the answer is just zero. Big fat zero. Don't even have to think about it. You can prove it if you want, but that's actually just zero. And next, from negative 2 to 2, arctangent x over a square root of x to the 4 plus 1. So how about this one? Dx. Arctangent is is that odd or even? Well, one thing we have to realize is that if f of x is odd or even, then the inverse of it has is also odd or even. In other words, it has the same property. So, for example, tangent x, is it odd or even? Tangent x is equals to sine x over cosine x. Cosine x, as we discussed earlier, is even, famously so. Sine of x is famously odd, actually. If you look at the graph, it's actually symmetric, but the other side is flipped. So flipped along the x-axis. So odd over even, this is an odd. Again, because there's only an odd number of odd functions. So uh, tangent x is odd. Therefore, its inverse, arctan, should also be an odd function. Alright? So the top is odd. How about the bottom? Well, we have f of x is equal to the square root of x to the 4 plus 1. What is f of negative x? Well, negative x to the power of 4 and then square root plus 1. Negative x to the power 4 is just x to the 4, since negative to an even power is just positive, plus 1 and the square root. So it's the same thing. So the bottom is even. So the integral, the answer is just 0. No questions asked, because it's odd over even. There's only one odds, therefore the answer 0. This doesn't work on every integral though, so be careful. Just test if each function is odd, even, or none of the above, because there are cases where it's actually just not even. All right, let's have another property. We need to prove that this f of x from a to b dx is actually equal to this from a to b f of a plus b minus x dx. So how can we do that? Well, let's first go to let's actually go here. Our We can have the next step to be let a plus b minus x is equals to u, right? So let's put a and b into x here. So if x is equals to a, so u is equals to a plus b minus a. Substituting a in, we get b. So if x equals a, u equals b. Same thing with x equals b. U is equals to a plus b minus b, which is equal to a. So we just flip. X equals a, u equals b. X equals b, u equals a. So let's put everything together. Uh, let's change the bounds of integration. So a becomes b, b becomes a. Great. And then this becomes u, right? And what about du? Well, let's find the derivative of both sides. One side is negative dx, the other side is du. So dx is equals to negative du. And then we multiply this by negative du. Again, the property of negatives is that we can switch the bounds of integration with this. So let's switch it up. Ba and then du. So we switch it up and then we remove the negative because that's how it works. F of u. Again, in here, u is just a dummy variable. This means that there is no difference between using u and then using x. Why is it a dummy variable? Because the bounds are the same. It's still a to b. All right. So the bounds are the same. Therefore, u can be exchanged for something else. And that something else could be like x. And we just proved that this is equal to this. All right. So that's the proof. And this is actually called the king property of integration. It's going to be useful in the next few questions. Question number 81. The integral from pi over 2 to 0, 1 over 1 plus tangent to the power of pi x dx. This looks outlandish, and it is, because there's a pi in the powers. If that was true, that it would be easy, because 1 plus tangent squared is just secant, and secant cosine, then we can do something about it. But it's pi, so we need to do something about this. What if we use King's property? How can we do that? So let's just do this. 1 over 1 plus tangent to the power pi of pi over 2 plus 0 minus x. So pi over 2 plus 0 is just pi over 2 minus x. So what's pi over 2 minus x inside tangent? How can we do that? Well, we can use the one of the integral no trigonometric identities with like the sum angle, but we're going to split it into sine and cosine. 1 plus sine of pi over 2 minus x to the power pi over cosine to the power pi of pi over 2 minus x. What is this? What is this? Let's remember what sine and cosine are. All right, theta. And let's label this as alpha. Let's label this as beta. This is a right triangle. So we know sine alpha is equals to let's label this A, B, and C is equal to A over C, right? So, and we also know that cosine alpha, beta, actually, is equal to also A over C. So, sine alpha is equals to cosine beta. And what is beta in terms of alpha? Well, the sum of the angles of a triangle is 180, and we already have two angles, 90 plus alpha. Plus beta actually. So that's the three angles, and then they all sum up to 180. Let's isolate B for a moment. Beta, so sorry. 180 minus 90 minus alpha. This is 90 minus alpha. 90 is degrees, and in radians it is pi over 2. So we know sine alpha is equals to cosine of pi over 2 minus alpha. So basically, this is because it's complementary. So alpha and beta should be complementary. Therefore, sine of alpha is a cosine of pi over 2 minus alpha. And the other side is true. Sine of pi over 2 minus alpha is also cosine alpha, right? So those are the properties that we need. So really, just maintain that. Really, these two just switch. So 1 over 1 plus this on the top becomes cosine to the power pi of x over on the bottom it becomes a sine to the power pi x. Cool. So that's the trigonometric identities. It's very important. So how about this? Well, what now? Well, let's fix it up by restoring like the tangent. So 1 over 1 plus this is now the cotangent or the reciprocal of a tangent. So that's it's just 1 over tangent to the pi x. It's just no complex fraction. What can we do? Well, we can multiply both the numerator and the denominator by x. Multiplying both the numerator and denominator is one of the more useful tools of calculus. So we get pi over 2, 0 to pi over 2, tangent to the power pi x over tangent to the power by x, since that is multiplied by 1, plus multiplying this and that, we get 1. And this, what does this mean? Well, just rearranging for a bit, we know that pi over 2, 0, 1 over 1 plus tangent pi x dx is also equal to tangent of pi x over 1 plus tangent pi x. And you say, yeah, great deal. So how? It's much hard. It's harder to solve now that the tangent is at the top and also at the bottom. What we can do here is to add them both together. So let me just move this, everything. So what we can do now here is to add these two together. How? Well, let's assign them the letter I, right? They are both I. So if we add I plus I, we get 2I, right? Let's add both of these together. The denominator is 1 plus tangent to the power pi of x. They are both the same denominator, so we can just add the numerator easily. So we get 1 plus tangent to the power pi x, then dx here. The numerator and the denominator, they can cancel each other out. And this is why it's so good. Because now, the problem has been reduced to just the integral of 1 dx. This is going to be equal to x, and then the bounds, we can apply them. The answer is pi over 2, but that's 2i. 2i is pi over 2. We have to divide both sides by 2 in order to get just I by itself, which is pi over 4. And I, we established earlier, was the original integral. 2. That looks like a 3. 2. 1 over 1 plus tangent pi x dx. This is equal to pi over 4. And that's the answer. So using King's property, we found the indefinite integral for this one. It looked hard, but it was actually possible. And it doesn't matter what the power is. I just used pi so that it's ridiculous, you know? If it's 2, it could be secant and cosine and whatever. But this, it's actually just, pi. I can use I can use a million, I can use any real number. I don't think imaginary numbers work, but I can use any real number and it just works. All right? It just works, you know. I can replace that with a Google or whatever. And the answer would still be pi over 4. Insane. So, next question, 82. The integral from 0 to pi over 2 again is sine squared x dx. You can use the power reduction formula that I discussed earlier, but you can actually use King's property here. It's actually really neat. Watch this. So, uh, for this one, you just insert the bounds inside the x. So pi over 2 plus 0 is just pi over 2 minus x dx. And this would be cosine squared x, right? This and that are both I, or the integral. So let's just combine them together. So sine squared x plus cosine squared x dx. This is just 1 again. So the king property actually allows us to reduce the problem to just the integral of 1. It's so good. And then the 1 just becomes x, and then pi over 2 to 0. Then the answer is pi over 2, right? And since this is 2i, we have to divide both sides by 2 in order to get the answer, which is pi over 4. And actually, this is just the same problem earlier, but now we got, but now it's just a square, so sine squared. Okay, the next question I will introduce the concept of something that was invented, or not invented, but uh, popularized by famous physicist Richard Feynman. Feynman's uh, technique. And not the Feynman technique of studying, it's just the Feynman's technique of integration. He didn't invent this, but he said it was unpopular, so why was it, you know? So here's the question. Just buckle up because this is going to be very long. So the problem is the integral of x to the 4 minus 1 over ln x dx from 0 to 1. Now, if you want to, you can try using just in finding the antiderivative. But I do think it's impossible, so we're going to use something very neat. We will let I to the power I of n, uh, which is now a parameter or a function, be equal to this x to the n minus 1 over ln x dx. So what does this mean? This basically means that if n equals 4, and then that's just the original integral, right? So we can manipulate this if we want. But at the end we want I of 4. So let's try getting I of 4. So the second step actually in finance technique is to find the derivative of I of n. And how are we going to do that? This is an integral. How do we find the derivative of it? Well, we can actually do this. The partial derivative of n, x to the n minus 1 over ln x. So the partial derivative of n means that we only focus on n. X is just a variable in terms of n, right? So we can treat x as like a variable. So the power of x to the n should be the derivative of x to the n is x to the n times ln x. That's how that's the exponent rule, right? So dx. So let's do that. 1, 0, and then x to the n ln x. The minus 1, this derivative is 0. So over ln x dx. So ln x has no n in it, so we're all good. The ln x and the ln x can cancel each other out, and we're left with the integral from 0 to 1 of x to the n. The antiderivative is simple. It's x to the n plus 1 over n plus 1. And then the bounds from 0 to 1. Now, this is equal to x, not n. So let's substitute x here. So 1 to the power of n plus 1, 1 to the power of anything is actually just 1 over n plus 1. And then minus 0, since 0. 0 on the top makes it all 0. So it's just 1 uh, to the 1 over n plus 1, right? So that's I prime of n. We need I of n. Okay? So that should be the integral of 1 over n plus 1, the n, right? And this is equal to ln of n plus 1. But we have an important distinction here to make because we need plus c, a constant. How are we going to find plus c? Because the answer later is going to be some number. It needs to be some number. It cannot be a number plus c or a number times c. No, we need to find what c is. And if you know your differential equations, if you've watched like a video about differential equations, you know how this works. But for those of you who don't know, let me walk you through it. This is I prime of n. Let's try to find a good value. Something that we know could be, we know the area, integral of. What is I of 0? Well, that is just the integral from 0 to 1 of x to the 0 minus 1 over ln x. X to 0 is just 1. 1 minus 1 is 0. So we know this is just going to be 0. Also, I of 0 is also ln of 0 plus 1 plus c. Ln of 0 plus 1 is ln of 1, which is ln of 1 is just 0. So this is just c. C and 0 are equal to each other. Therefore, c is equals to 0. So we can safely ignore c. Just put 0 in it. There. We just put 0 in it. And that is going to be I of n. C is equal to 0, so there's nothing there. So we just need to find I of 4. And what is I of 4? It's just ln of 4 plus 1. This is going to be ln of 5. And that is the answer. Richard Feynman has done it again. Right. This was question number 83 for your information. And question number 84. The integral from 0 to infinity of sine x over x. This is actually impossible to antiderive. There is a special function for this. It's called the sine integration, sine integrator, I think. But we don't need to find the antiderivative, or maybe we need later. But what we need to do is actually to multiply it by e something. Let's do the Feynman thing again, but this time we need to be creative. We need to multiply this by e to the negative sx. S is going to be the parameter here. Dx. Anyone who is in the field of signal processing or whatever will know what I'm doing here. But we can actually just try this. So like Feynman's technique earlier, I prime of s, we just need to find the partial derivative inside the integrand in relation to s. There. So what's the derivative of e to the negative sx? Yeah, in respect to s. Well, it stays e to the negative sx, but chain rule, we need to multiply by the derivative of e to the negative sx with respect to s. So that's going to be negative x. And then multiply by sine x over x dx. So x and here cancel each other out. We get negative integral from 0 to infinity of negative, sorry, that's right, e to the negative sx sine x dx. And from here we can actually use integration by parts in order to find the answer. So let's put the d, let's put e to the negative x steps under d and sine x under I. So derivative, this is now with respect to x. It's negative s e to the negative sx, negative cosine x here, and then positive s squared e to the negative sx, negative sine x here. That integrate. So e to the negative sx cosine x, minus 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 is minus uh, s e to the negative sx sine x. And that we have to substitute infinity and 0 here. Infinity is not a good uh, infinity, but you can find it overall. Just let's try evaluating the value later. So, then the next one is just plus, and then actually minus, and then s squared is just a constant. The integral of e to the negative sx sine x dx. And then, actually, there's a negative here. So this all has to be flip the sign. So we just flip the sign here because there is a negative on the outside here. So yeah, we just flip the sign. And now what? Well, first of all, let's find the actually we don't find the this first because we haven't found the actual antiderivative yet. Let's just find the let's just find the antiderivative first. Totally. Infinity. 0 to infinity here. Okay. So we can transfer that integral to the other side. We will get let me remove the di thing. We're done with this. We will get uh -1 minus s squared equal, then integral of, from 0 to infinity, e to the negative sx sine x dx is equal to e to the negative sx, which should be negative, cosine x plus se to the negative sx cosine x. So we just divide both sides by negative this, but basically just this. So this is negative 1 plus negative 1 plus s squared. So that's why we divide both sides back. So we can remove this. And yeah, let's apply the x equals 0 and x goes to infinity. So as x goes to infinity, this one and this one goes to 0, since there's 1 over e to the sx. And if the bottom is infinity, the entire thing is going to be 0. I covered that in the 75 calculus one. Basically, this is just going to be 0. So this is we can move this outside. And then let's evaluate everything. So as x goes to infinity, this is both 0. Okay? Cosine and sine of infinity is basically just hovering around -1 and 1, so it doesn't really matter. So if x equals 0, uh, the sine of 0 is just 0, and then cosine of 0 is actually 1. And e to the 0 is 1. So this is actually -1. -1. Yes. Hold on. Remember, look at this. The negative sign here actually should be on the other side. Why? Because the original question was actually a negative here. There's a negative here, and so there shouldn't be any uh, negative sign on the other side. Sorry about that. So negative that this should be equal to this. This is -1, so the answer is negative 1 over 1 plus s squared. So the answer earlier is -1 over 1 plus s squared. Let's move down. Let's move all of this down. All right. So negative integral of infinity 0 e to the negative sx sine x dx is equal to -1 over 1 plus s squared. This is the original one. This is I prime of s. All right. So this is I prime of s. We just need to find I of s, which is the integral of -1 over 1 plus s squared ds in terms of s. This is just negative arctangent of s, and then plus c. And if you know your uh differential equations, you know how to find plus c again. But again, we just go to the original equation. I of s is equals to sine x over s e to the negative sx infinity to 0. What can we do? Actually, we can just put I to the infinity here. It's not good. Not good method. You know, you actually need to find the limit as s goes to infinity. But the shorthand is just I to the infinity. What is this? Well, e to the negative infinity is going to be 0. So the whole thing is going to be 0. Therefore, the value is just 0. Hmm. So the value is 0. So I of 0 is equal to 0 on one side. And then the other side, it's the negative arctangent s plus c. So what's in infinity? Sorry, infinity. So what's negative arctangent in infinity? This is actually pi over 2. All right, negative pi over 2. So this means c is actually pi over 2. So moving everything. All right. Since c is a pi over 2, I of s is negative arctangent s plus pi over 2. And remember the I of s is actually this. Remember that? So the original function is sine x over x. This is sine x over x, e to the negative x. If s is 0, so I of 0 is actually the original sine x over x. Since e to the 0 is just 1. So so we need to find the value of I of s as s goes to ss is 0. So I of 0 is equal to negative arctangent of 0 plus pi over 2. Arctangent of 0 is going to be 0. Then we add pi over 2. I of 0 is pi over 2. In other words, the integral from 0 to infinity of sine x over x is equal to pi over 2. And that's an amazing result, actually. This is called the Dirichlet Integral, sine x over x. There's also sine squared x over x squared, but that's a story for another time. It's also pi over 2. And the cubic version is different. All right. We are now in the realm of double integration. So let's proceed with question number 85. The integral from 1 to 2 of the integral from 0 to x of x squared y dy dx. Now we are now deep into integration. We're so deep, in fact, that we're doing two integrals in one. So how do we go about doing it? Well, if we integrate in with relation to dy, it means we're only integrating y. We're for, we're ma- uh we're thinking of x as a constant. So for in the y world, yeah. So let's do that. Uh just integrate the y thing first. So the integral of y is just y squared over 2, and then x squared is just sitting alongside it. And then we are substituting from 0 to x. And then let's just put the rest here. This is going to be the integral from 1 to 2 of x squared times x squared over 2 minus 0, but that's just 0, and the x. This is the integral from 1 to 2 x to the 4 over 2 dx. Okay. That the integral of this is x to the 5 over 10, and we're finding the value from 1 to 2. 2 to the 5 is 32 over 10 minus 1 to the 5 is 1 over 10. The answer will be 31 over 10. That is the answer for double integral. The double integral is actually describing the volume of a certain solid. 86. The integral from 0 to 1 of the integral from pi y to pi sine x over x dx dy. So this is actually a question from another YouTuber, Black Pen Red Pen. Link in the description if you want to see that. But let's try answering it for ourselves. So what we can add, sine x over x does not have an antiderivative that is elementary. And earlier it was torture to even find the integral sine x over x as x goes from 0 to infinity. What do we do about this? What we can actually do is to flip dy and dx. So what if we started integrating with respect to y? But that's dangerous because just flipping it might not be enough. We need to actually change the bounds of integration. We need to make sure that it all lines up. So how are we gonna do that? Let's draw the Cartesian plane properly, something like that. And this is actually x equals pi. So x equals pi, then x equals pi y. right? Then y equals 1, y equals 0. These are the four functions that we need to graph. So y equals 0 is just this. Y equals 0. Y equals 1, let's draw it like this. This is y equals 1, and then this is y equals 0. Put somewhere actually. Here. So what we can do is we need to do x equals pi. So x equals pi looks like this. So this is pi. Okay. And x equals pi y is also y is equals to x over pi. Right? If x equals pi, then y equals 1. So it lands here and at 0. Something like that. All right. So those are the graphs. All right. What do we need to do here? Well, we need to find what area this is describing, what region it is describing. So it says here from 0 to 1 in terms of y. So y is the y-axis is actually this one. So we need to describe an angle, the area from 0 to 1. So from here to here. So that is the bounds. Okay, that's number 1. Number 2 is from x equals pi y to x equals pi. This is x equals pi y. They say it goes up until x equals pi. Right? So it goes from 0 to 1 and then x equals pi. This triangle here is the area that we're trying to represent. This is the region of what we're trying to represent. And this is kind of the shadow of the function that we're trying to graph. And this is just the bounds, actually. So it's the shadow. What we can do next is to switch it up. So dy at dx. That's what we want, right? But what would be the bounds? So in terms of the y, we would actually start from here. No, from 0. Let me just remove the bars. No, actually, no, never mind. Okay, so let's erase all of it here. So in terms of the y, we're actually trying to find this area, right? So we're starting from here and we're going up until this line. We're gonna go until 1 because, stuff, so and so. So we can stop at this line. What is this line in terms of y? Well, it's x over pi. So we can say we're going from 0 to x over pi, right? And then as in terms of x, we're going from a 0 to pi. Yes, actually, that's correct. Right? So we're going from 0 to pi. It's say, well, this is not included. Well, 0 means here, and then going to pi means going there. So it doesn't have to start at the very start. We just kind of go there. We just kind of blocked it from being the area because of the y value inside. So let's try integrating sine x over x in terms of y. This is just actually y times sine x over x. And then just x over pi, and then 0. Let's put the bounds as well here. We need to substitute this into y, so we get x over pi times a sine x over x. X 0 times sine x over x is just going to be 0. So let's we can ignore that safely. So x and x cancel each other out. We get pi 1 over pi is actually a constant, so let's put it outside. Then sine of x dx. The antiderivative is just negative cosine x. And then from 0 to pi. Now, cosine of pi is negative 1. So negative of negative 1, let's put everything in. Negative 1 is just positive 1 minus negative 1. Cosine of 0 is 1. So we get this is actually just a 2. So the answer is 2 pi, 2 over pi. So the reciprocal of the answer earlier, pi over 3. So that's actually the answer, 2 over pi. Cool. Next question. Question number 87. The integral here, 0 to 1 over square root of 3, from 0 to pi over 6. No, not 0 to pi over 6. Arctangent, next. And secant to the power 6, uh, dx. So it's actually good to flip it first. So let's try flipping flipping this. So what is the graph? Well, secant y is actually this graph. Uh, it's this, right? You can check Desmos and see if that's correct, but this is the graph of secant. And then let's draw it properly. As properly as I can. So from here, then ring, yeah, all right. Then it's an asymptote. The asymptote is actually pi over 6. And this is actually arctangent x. So we are trying from 0 to pi over 3. So from 0 to actually not asymptote. Asymptote is something else. This is let me clear that again from the start. Sorry about the confusion. Let's graph it first. So we're graphing the bounds here. First, we're going to do this. Yeah. So this is going to be pi over 6. Right? All right. So this is 1 over square root of 3. So this is x equals 1 over square root of 3. And then x equals 0 is the y-axis. So from here to there, right? And from arctangent to pi over 6. So the area, the region we're trying to find is actually this. So in changing to dx dy, in order to integrate it better, we need to find something that can the bounds of x. So how can we find the bounds of x? Well, x actually starts from here. So it starts at 0. And then it goes up until the arctan x line. But we can say it's arctan x. We need to base it in terms of y or constant. Well, luckily enough, this is actually x equals tangent of y. So we can just insert tangent of y here, right? And then from 0, the y value goes up to pi over 6, which is this one. All right. Again, it's this until that. So yeah. Okay. Mm, let's try to find the integral of secant to the 6y. We get x to the secant 6y, and then we need to distribute tangent y and 0 here. And then, yeah, 6. So so that's going to be the integral. So tangent y, we just insert it here. 0, it just all becomes 0, so we can ignore that. So this is just a single integral. So this is very simple, actually. So how to solve this, we need some sort of secant squared, and we can get secant squared here. So tangent y, and then a secant to the power 4 y, secant squared y dy. Tangent y is derivative of secant squared, so we can use that for substitution. We know secant squared is just 1 plus tangent squared y. But this is to the fourth power, so we just square that. Let tangent y be u. Secant squared y dy is du. Okay? Y is equals to pi over 6. U should be equal to 1 over square root of 3. Y is equals to 0, u equals 0. So the integral becomes this. A 1 over 3 returns, a 1 over square root of 3 returns yet again. And tangent becomes u times 1 plus u squared uh, du. And let's move everything up so we can move everything up. So we can write. So from here we can just expand this to get u times 1 plus 2u squared plus u to the 4 du. Again, let's just evaluate this algebraic expression. Then integrate it. So the integral is u squared over 2. And then the integral is 2 over 4 u to the 4. Although 2 over 4 is also 1 half. Plus u to the 6 over 6. Then from 1 over square root of 3 to 0. 0 to 1 over square root of 3. Evaluate it all together. You can calculate it for yourself, but the value is actually 37 over 162. If you find something, let me know so I can correct it next video. But that's pretty much the answer. Question number 88. Double integral, and then there's R no R there. X squared plus y squared dA, right? R is the region bounded by the unit circle centered at the origin. So we have R, and R is basically a marker of the region. So it's not like bounds like earlier, but it's still we can check what it is. So it says here that R is the region bounded by the unit circle. So this is it. And then the center is at the origin, and then like everywhere it goes, it's just one. So it's a circle with radius one. So how do we do this? Well, we're going to be doing something called the polar substitution. The polar substitution basically it tells us that we need to substitute x and y into something else. So x will turn to r cosine theta, y is equals to r sine theta. If you know your polar coordinates, you might know this. R is the radius of a point. So for example, this. Instead of using x and y coordinates, we're going to use r, which is the distance from the center, and then the angle, which is going to be theta, right? So those are the two coordinates in the polar coordinate system. So it's different from the Cartesian coordinate system. So that's what we're going to be using. And in order to find the replacement, dr d theta, because dA is dx dy here because it's x and y, in here we need dr d theta. So dx dy, and then we turn that into dr d theta. And it's not easy in order to find what it is. We need to use the Jacobian determinant using a matrix in order to do it. If you don't know anything about matrices, it's fine. This is just a simple structure in our Jacobian term, double integrals. Most of matrices don't even apply here. So The matrix is the partial of x with respect to r, the partial of y with respect to r, the partial of x with respect to theta, and then the partial of y with respect to theta. Then we multiply the diagonals and then we subtract them together, find the absolute value, and then we can go do our own thing. So the partial of x with respect to r, the derivative r is 1, so what remains is cosine theta. The partial of x with respect to theta, cosine theta derivative is negative sign, so it's negative r sine theta. The partial of y with respect to r derivative is 1, so it's going to be sine. And then partial of y with respect to theta, this is going to be r cosine. So we can use the for the determinant. We just need to find the determinant. We get r cosine squared theta minus negative r sine squared theta. And we find the absolute value of that. We get r, this is r, yeah. R cosine squared theta, we can, plus sine squared theta. This is just 1, so this will be r. So that's the determinant. That is what we're going to be introducing. So how do we the determinant? Well, we now know dx dy is equals to dr d theta. All right? So that's good enough. But how can we use it in order to find the integral? Here goes. The region that was specified by r is the unit circle, right? So the r, or the radius, must be from 0 to 1. So the dr comes first. So r must be from 0 to 1 because it starts at the origin, it ends at r equals 1, which is the radius. And then the theta, which is the angle. So it starts from 0 and then it loops back to 2 pi because it's a complete circle. So it's 2 pi. And what about x squared plus y squared? What do we do with that? Well, we just apply this. So x squared, which is going to be r squared cosine squared theta, then plus y squared, which is r squared sine squared theta. This becomes r squared cosine squared theta plus sine squared theta. This is going to be equal to 1. So r squared times 1 is just r squared. Multiplied by the Jacobian determinant, r dr, sorry, r dr, d theta. And that's the setup. That is the polar coordinates. So just combine these together, we get r cubed dr d theta. R cubed becomes r to the 4 over 4, and then 1, 0, d theta here, then 2 pi, 0. Okay, so let's try finding, let's try just substituting 1 and 0 here. So we get, 1 over 4. 0 over 4 is 0, so that's fine. Integral from 2 pi, 0 to 2 pi. So the answer is going to be theta over 4, and then we just substitute 0 and 2 pi here. So we get 2 pi over 4 minus 0, so 0. The answer is going to be pi over 2. So always says pi over 2. And that is going to be the answer. Question number 89. The integral from 0 to infinity of e to the negative x squared dx. What is this? This is just a single integral, but what can we do? Well, this is actually the famous Gaussian integral. So let's say this is I. If we change the letter, it wouldn't matter much, right? After all, it's the same thing. So let's just multiply them together. So I times I is I squared. So we just combine the integrals together, and look, we have a double integral. So we can combine them together to form a double integral. Actually, there's two more steps before that, but essentially you can do that. All right. Okay. So the region that this is describing is from 0 to infinity, then from 0 to infinity. So the entire first quadrant, basically. So yeah. Let's combine this together. Let me just put r here. R is equal to that. So it's just a shortcut. Like negative x squared minus y squared dx dy. X squared, negative x squared minus y squared reminds me of polar substitution, like the one we did earlier. X squared plus y squared and polar and whatnot. So what we're going to do here is just going to polar sub. I'm not going to pull the Jacobian determinant. We already know what dx dy represents. So r d theta and then e to the negative r squared. That's the polar sub of x squared plus y squared, as we discussed earlier. And we need to find the bounds of R. So here, we can see that it actually extends from 0 all the way to infinity. So no shot goes to infinity, right? And then the angle, it actually goes from 0 to just 90 degrees, which is pi over 2. Appears everywhere, man. So pi over 2 is what we're going to be using. All right. So let's use substitution. Let r squared is equals to u. Mm. We can use this. The substitution with the substitution. We'll thought of that. Anyway, r is equals to infinity or approaches infinity. U also approaches infinity. R equals 0. U is also 0. So no change in the bounds. E to the negative u and then over 2 actually, since 2r equal dr is equals to du, then r dr equals 1/2 du. All right, so we got 1/2 here, and then we just retain the bounds on the outside. No change there. This becomes negative e to the negative u over 2 from infinity to 0, and then the bounds of the outside. So maybe move it up. Move up. Okay. So infinity going here, e to the negative infinity, 0. Okay? Going to be, okay, 0 minus, and then negative, e to the 0 is going to be 1/2, and then d theta. This is positive 1/2. Let's put it outside. We can actually put it outside. Then d theta. So this is going to be theta over 2, then pi over 2, 0. The answer is pi over 4. Right? Pi over 2 times 1/2 is pi over 4, and 0 is just 0. So this is I squared, as I said earlier. This means that we need to find the square root of both sides. And just the positive, because we're finding a positive area. So the square root of pi over 4 is the square root of pi over 2. This is the famous Gaussian integral, as I said earlier. And it's actually a neat result, don't you think? Square root of pi, like square root of pi. All right, sure, whatever. No, that doesn't normally exist, but let's roll with it. Question number 90. The integral from 0 to infinity of e to the negative x squared, cosine 2x dx. Okay. Uh, let's say this is I. Okay. And then maybe we can use Feynman's technique here. Let I of A be equal to this. Why do I want to use Feynman's technique? Because there's a cosine in here and I want to extract the x from it. Maybe we can use the chain rule in order to get the x. Then maybe it's easier to find the integral of uh, everything else when everything comes to pass. So what is the derivative of this? What is the next step? We find the derivative. Okay. So the partial with respect to a, e to the negative x squared cosine ax dx. We get this is going to be e to the negative x squared stays the same. Multiplied by derivative of this entire thing. So it's negative sine of ax multiplied by the derivative of the inside, which is going to be x dx. So x to the negative x squared sine ax negative outside somewhere at the x. Okay, I can use the DI method in here. di. Since it's already negative, let's put negative first here and then positive the next. So, oh, hmm. Actually, no, 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 no. The negative is actually part of the integral. Okay, so let's put just put negative here. Lump it in with that. So we can use the usual positive negative. Thank God. Sine x, sine ax, put it in the d, and then for the I, we just put negative x e to the negative x squared. All right. Derivative of sine is cosine, then ax, and then multiply by a, since that is we're differentiating with respect to x. And then for this one, uh, this is 1/2 e to the negative x squared. If you realize, this is x, so the derivative of x squared is 2x, then there's negative, so that's 1/2 e to the negative x squared. So we can do this. 1/2 e to the negative x squared sine ax. And then let's find the values from 0 to infinity. And then subtract by 1/2 a, or a over 2, e to the negative x squared cosine ax. This is going to be 0. This is going to be a over 2, the integral of e to the negative x squared cosine ax. Right? Let's reformat it in a way that we can understand. I prime of a is equals to 0. So negative a over 2. This is actually just I, normal I of a. And some of you may realize, oh, this is just a differential equation. So if you know the differential equations, you can solve it. If not, just follow me for a moment. Next step would be dividing I of a from both sides. So over I of a equals negative a over 2. Right? Let's find the integral of both sides with respect to a. This is the derivative of something over something. Immediately, that's ln of I of a. This is equal to negative a over 2. This is negative a squared over 4. Okay? Plus c. 1. Okay? C1 means the constant is not complete yet. It's not the final yet. So, let's raise e to both sides so we can isolate I of a. We can cancel each other out. That I of a is equals to e, uh, first, e to the c1. This is actually e to the negative a squared over 4, e to the c1. E to the c1, c is a constant, right? C1 is a constant. E to the c1 is also a different constant. So we can call it c2, e to the negative a squared over 4. So this is actually good. And since this is the final answer or final-ish answer, we can remove the 2. So it's just c times e to the a squared over 4. C is a constant. So let's move it up. This is gonna be a big boy. So we need to find I of 2, but we need to first find c. What is c? Well, let's go back to I of a. This is again e to the negative x squared cosine ax dx from 0 to infinity. So If a is 0, this is now equal to I of 0 equals infinity e is 0, e to the negative x squared. Then cosine of 0, this becomes 0. So cosine of 0 is just 1. So we can just multiply it by 1 and it's going to be e to the negative x squared. This is the result earlier, square root of pi over 2. And why I put it here instead of earlier? Because the result of this is actually very important. So, I of 0 is square root of pi over 2. I of 0 is also c times e to the negative 0 over 4. This is going to be just 1. So it's going to be c. So c is equals to square root of pi over 2. And indeed, that is going to be what the constant is. So I of a is square root of pi over 2 times e to the negative a squared over 4. That is it. That is the general of I of a. Now we just need I of 2 because that's the original one. Remember? I of 2 is going to be square root of pi over 2 e to the negative 2 squared over 4. 2 squared over 4 is just going to be 1. Since 2 squared is 4 and uh 4 over 4 is just 1. So e to the negative 1 is 1 over e. So the answer is square root of pi over 2e. This is the answer. It's actually pretty cool, you know? There's pi, there's the square root of pi, and then e on the bottom. It's kind of cool. So that is going to be the answer for question number 90. And the next part is going to be Laplace transform. So we will go there now. Let us proceed to the next part. The next part, we will be tackling the Laplace transform. So what is the Laplace transform? It is a method used to process signals such as sine waves and whatnot, and it is the counterpart of the Fourier transform. Although this is more versatile than that, and we can also use that in differential equations in pure mathematics and so on. But for today's video, we're going to just process some Laplace function. So, the definition of the Laplace transform, the Laplace of f of t, this is equal to the integral of e to the negative st f of t dt as t goes from 0 to infinity. So this is the Laplace transform. We will be using this later on in maybe if you are an engineer, you will use both the Laplace and the Fourier transforms in order to do that. Computer science majors and all sorts of stuff. So it's very important. But for now, let's just focus on the mathematics. 91. Question 91. The Laplace of e to the AD. There we go. Pardon the crude symbols. But let's just use the definition here. The definition is e to the negative st, e to the at dt. To solve this, we can use the laws of exponents and whatnot. So let's do that. Let's combine the exponents. We can add them together since they have the same base. There. All right. After this, we can factorize t out in order to get this. All right. So it's form e to the something, then t. And what we're actually going to do here is to factorize the negative as well. So it will be like this. Negative s minus a, then t dt. Then we can calculate for the antiderivative of this. We will get, well, e to the negative s minus a t. And then to combat the chain rule, to nullify it, we go negative 1 over s minus a. Something like that. And then let us substitute t equals 0 and t approaches infinity. So if t approaches infinity here, we will get, let's put 1 over s minus, negative 1 over s minus a on the bottom, on the front. And then, putting infinity into e to the something t, putting infinity in there will result in 0. Again, e to the negative infinity is 1 over e to the infinity. It's 1 over infinity, which always goes to 0. That's what it is. So that's going to be 0. And e to the 0 is just 1, so we subtract 1. So this is going to be negative 1. There's a negative here. Negative of negative is positive. So you get 1 over s minus a. We need to have a restriction that says s minus a is greater than 0 or s is greater than a. Otherwise, this won't work. 92. We are tasked with computing both the Laplace of cosine of bt and Laplace of sine bt. You can say that's two questions. Why is it one? Well, we do know that from Euler's formula that e to the I bt is equals to cosine bt plus I times sine of bt. This is the famous Euler's formula, which is a result from the Taylor series expansion, Maclaurin series expansion of e to the x, cosine x, sine x, and using imaginary numbers. But yeah, that's also the famous result e to the I pi equals negative 1. So there's that. What we're going to do is to find the Laplace of e to the I bt. Right? So the Laplace of e to the at, remember, the Laplace of e to the at equals 1 over s minus a, right? So this should be the same, 1 over s minus, and then since the a and the ib represent the same thing, this should be ib. Let's erase this. So that's going to be it, all right? Let's try to remove the imaginary unit on the bottom by multiplying it by the conjugate, since this will be the uh, difference of two squares. So on the top is just s plus ib. On the bottom will be s squared minus I squared b squared. So I squared is negative 1, so it's negative of a negative. So s squared plus b squared will be on the bottom. Separating the real and imaginary, here we get s over s squared plus b squared plus I times b over s squared plus b squared. All right? Since cosine bt is the real part, we can say cosine of bt or the Laplace of cosine bt. Yeah. So it's going to be s over s squared plus b squared. While the Laplace of b over s squared plus b squared is equals to b over s squared plus b squared. I messed up. No. The Laplace of sine The Laplace of sine bt, sorry, is equals to b over s squared plus b squared. There we go. Oh my god. Okay. So this is because this is the real and this is the imaginary part. Okay? And there we go. Question number 93. The Laplace of cos bt, ct, right? We're going to use c here. And the Laplace of cos sinh cd. For here, we're gonna use the fact that cos uh, ct is equals to e to the ct plus e to the negative ct over 2. And then that sinh is equals a ct is equals to e to the ct minus e to the negative ct over 2. So that's cosh and sinh. So let's try processing them together. So, uh, so let's try finding the Laplace of e to the ct plus or minus e to the negative ct over 2. Why did I use plus and minus? So we can do this together instead of separately. They're going to be similar operations anyway. So we can actually put the any constants to the outside. So we can put 1/2 on the outside of the Laplace, leaving us with e to the ct plus or minus e to the negative ct. And additionally, we can also separate Laplace transforms that are separated by addition or subtraction. And this is addition and subtraction, so we can do this. Plus or minus, don't forget that, Laplace of e to the negative ct. On the left side, we get 1 over s minus c, then 1/2 here, because of the Laplace of that. Plus or minus 1/2 of the Laplace of this. So if this is s minus c, this should be s minus negative c, or 1 over s plus c. We need to combine these two together, so let's factorize 1/2 here, and then just process these together. So we got s plus c plus or minus s minus c all over s squared minus c squared, which is this difference of two squares on the bottom. Just multiplying the yeah. So adding them together is the cosine version. Subtracting them together is the sine version. Caution sinh. So adding them is the Laplace of cosh, which is equal to s plus s plus c minus c. So the c's cancel each other out. The s's don't become 2s. And 2s and 1/2 here, the 2 cancel each other out. We get s over s squared minus c squared. And for the Laplace of sinh of ct, similar thing. So the s minus s cancel each other out. The c minus negative c becomes 2c. And 2c, the 2 and the 2 cancel each other out. We get c over s squared minus c squared. Much like earlier, but this time there is a minus. So those are the answers. Question number 94. The Laplace transform of the mu function of t minus a, where mu of x equals 1 if x is greater than 0, and mu of x is 0 if x is less than 0. So it doesn't exist for x equals 0. So what is this going to be? Well, let's split the Laplace into two parts. Because this is the integral from 0 to infinity of e to the negative st mu of t minus a, correct? So let's split this into two parts. First part is when t minus a is greater than 0, and then second part is t minus a is less than 0. This means t should be greater than a, and t here is less than a. Right? These are the two parts. So, how can we do that? Suppose a, mm, suppose a is greater than 0. Let's assume this fact. All right? Mm, because our bounds are from 0 to infinity. So a can only really be 0. If it's negative, well, doesn't make sense. Or all of it is going to be included. But let's assume a is greater than 0. This first part, from 0 to a, this is where t is less than a. a minus maybe, just a e to the negative st times 0. Since if t is less than a, uh, mu of x would be 0. Again, t minus a is less than 0, that would be mu of x is equal to 0. The next part is from a to infinity. E to the negative st multiplied by 1, since that is again mu of t minus a. So, this is just 0, since the integral of 0 is just 0. Because y equals 0 is just the y-axis, and there's nothing below that that's also in the middle of the y-axis. It is an x-axis. So, there's nothing in between that and the x-axis. So, yeah, it's just 0. So, yeah, the first part is 0. The second part is the one that's important. Because it has e to the negative st times 1. So the antiderivative is negative 1 over s e to the negative st. So we just insert infinity and a here. Infinity going into the exponent in here. E to the negative infinity, that will be a 0. Minus negative 1 over s e to the negative sa. Negative negative gets a positive, so the answer would be e to the negative sa over s. And that's the answer. Again, we assume a is positive. 95. The Laplace transform of t to the n. You can use the Laplace definition, but for this one, we're actually going to use something interesting. Okay, so remember the Laplace. Recall that the Laplace of e to the at was equal to 1 over s minus a. Alright? And that e to the x is also equal to n equals 0, the sum from n equals 0 to infinity of x to the n over n factorial. This is the Taylor series or the Maclaurin series, whatever you want to call it, power series, a representation of e to the x. So that's going to be important. How is it going to be important? Well, let's try to find the Laplace. Let's try to find the Laplace of e to the at as a sum. Here's how we're going to do. So in the middle, we get Laplace of e to the at, alright? On the right-hand side, we know that this is 1 over s minus a. On left-hand side, sorry, the left-hand side. On the right-hand side, however, we need to realize that we are finding the Laplace of the sum from n equals 0 to infinity of a to a times t to the power n over n factorial. All right? So, what are we going to do after this? Well, first off, let's process this thing. I want it to the form something 1 over 1 minus something. So let's try processing it. I will multiply it by 1 over s, both the numerator and the denominator. This will be 1 over s times 1 over 1 minus a over s. Why is that important? Because this is the infinite geometric series formula. The infinite geometric series formula is for a sum of uh, a r to the n. This is a over 1 minus r. This is the infinite geometric series sum. So if a is 1, then this is going to be 1 over 1 minus r. 1 minus 1's something is exactly what we have on the left-hand side. So let's try expressing that side in terms of a sum. Same bounds. And then A is going to be 1, so no A. We can just ignore it. Then A over S is going to be the R to the power n. And then for here, let's actually process this first before moving on. So the Laplace of the sum, everything that is not part of t, we can actually move outside because the Laplace is just focusing on the t because the other variables, constants, are just constants in relative to t. So let's process this. The sum from n equals 0 to infinity, a to the n, t to the n over n factorial, and then the Laplace of this. T to the n is the only important part, so we can Laplace that on its own. And then the sum can go outside a to the n over n factorial. All right. So let's do that. So this becomes sigma from n 0 to infinity a to the n over n factorial times the Laplace transform of t to the n. Laplace transform of t to the n is exactly what we want. So how can we equate these two together? Let's process it even further by separating the a and the s here, loss of exponents, a to the n over s to the n. And there's 1 over s here, so we can add 1. So s to the n plus 1. Again, loss of exponents. Let me just... There. This is equal to this. A to the n over n factor. Laplace of t to the n. Look at this. A to the n, a to the n. They're both in the numerator, they're both there. That means everything else must also match. So let's just compare 1 over s to the n plus 1. This should be equal to Laplace transform of t to the n over n factorial. Multiply n factorial to both sides, we get the Laplace transform of t to the n is equals to n factorial over s to the n plus 1. This is the answer. A. And from here, you can essentially prove that 1 half factorial is square root of pi over 2, I think. You can use the Gaussian and whatever, like substitution, then Gaussian. But I'll leave that to you to prove that 1 half factorial indeed is square root of pi over 2. So that's an amazing fact. 96. The Laplace transform of e to the at f of t. So let's introduce some new notation in the Laplace notebook. The Laplace transform of f of t. This is equal to this, right? So e to the negative st f of t dt. We can also introduce the new notation big F of s. S is this thing right here. So this can be a notation. This and that, they are the same thing, but they refer to different stuff. So if you see big F of s, Laplace of f of t, they're the same thing. So let's try doing it. Let's try doing this. This is going to be the Laplace of e to the at ft is going to be the integral from 0 to infinity e to the negative st e to the at f of t, right? Dt. So let's combine the exponents like last time. To the negative, I'll put it outside. Then s minus a t. So it's much like question number 91. This is that. So f of t dt. We have e to the something t f of t dt. let's try putting the big F notation here. Big F of S minus A. This is another way to interpret uh, the Laplace transform of this. So e to the at f of t is just equal to big F of S minus A. So what we do is just use the Laplace transform normally, and then just put S minus A where S should be. I will introduce it in question 97. The Laplace transform of e to the 2t cosine of 3t. So remember the uh, f of s, or the Laplace transform of cosine of 3t. Remember the Laplace of cosine is if you just look back, s over s squared plus v squared, right? So what we can do here is just to substitute the b here. So it's going to be s over, sorry, this is going to be s over s squared plus 9, right? So let's insert s minus a. It's because we have e to the 2t here. This is going to be f of s minus 2. This that, right? Because of the question 96. So this becomes s minus 2 over s minus 2 quantity squared plus 9. Let's process this. So s minus 2 over s squared minus 4s plus 4 plus 9. Or s minus 2 over s squared minus 4s plus 13. I don't think we can further uh, quantify or simplify this, but yeah, that is question number 97. Question number 98. The Laplace of t of f t. This is not the game, but this is rather Laplace. So let's just use the definition first. Yes. So what are we going to do here? Well, let us just observe this. Let's put just words here. Observe. All right. So the Laplace of f of t, by definition, this is just e to the infinity e to the negative s t f of t dt. We call this f of s, right? F of s. So what we're actually going to do here is to do a Feynman and then just find the derivative of f of s. So much like Feynman's technique, we just find the partial of s here, right? So the partial here is going to be, mm, well, e to the negative st stays, but we're going to have to do the reverse chain rule. We have to mitigate the chain rule, so we just put negative 1 over t, right? Then f of t, negative, sorry, no. We have to do the chain rule, not the reverse chain rule. Because this is the derivative, I forgot. The negative t, that spells out test. Nice. F of t dt. All right. Let's put the negative on the front. E to the negative st, let's put t here, f of t dt. And look at this. That in here, this is the Laplace of t ft. And there's just a negative here. So f prime of s is equal to the Laplace of t f of t. All right? And this is the f of s. Okay? So the Laplace, negative f prime of s. Negative Laplace of t f of t is going to be negative the derivative with respect to s of the Laplace of f of that is the answer. Or maybe you can just put the negative on the other side, but that is the interpretation of it. All right. Or maybe you can just put f of s here, but that is the formula. Question number 99. The Laplace of t sin ct. Which is what we solved earlier. Sinh of ct, remember, recall, Laplace of sinh ct is equal to c over s squared minus c squared. So the Laplace of t sinh ct is the derivative or the negative derivative of a c over s squared minus c squared. So this is going to be negative the derivative of c times s squared minus c squared to the power negative 1. Right? We can use chain rule here. So negative goes the front. So negative of negative 1 times c times s squared minus c squared to the power of negative 2 multiplied by the derivative inside 2s. Negative negative turns into positive. C remains here. Yeah, sorry. 2 and s go here over s squared minus c squared squared. All right, let's write it properly this time. So it's going to be 2cs over s squared minus c squared. Okay, that's the answer. Nice. For the 100th question, finally, the Laplace transform of f of t over t, what is that? Well, let's define this as the new big F of s. All right. This is equal to 0 to infinity, then f of t over t e to the negative st dt. What we're going to do here is to make an observation first. The integral, let's say the integral of, we want the integral of like e to the negative st ds. That's going to be uh negative 1 over t e to the negative st. So there's t on the bottom here. That's one way to do that. But we need some bounds. This is where the fundamental theorem of calculus comes in handy. Earlier we got the fundamental theorem of calculus in terms of the derivative. Now this is going to be in terms of the integral. So this is the other definition of the derivative. For example, we got this. Mhm. We got this. The answer here would be a big f of x, right? So that is the other fundamental theorem of calculus. But we're something similar, but not quite. We are going to use a definite integral. So we can insert that seamlessly into the definite integral that we're already trying to solve. So let us integrate e to the negative, let's say u t, right? We want this to be, we want this to have like going to 0 and then maybe s later. So if t goes to infinity, we know that goes to 0 and then maybe on the bottom we have an s. What happens here is that this is the antiderivative, and then we just insert infinity and s here. Inserting infinity into this, we get 0. And minus negative 1 over t e to the negative s t. Two negatives make a positive, so the answer becomes e to the negative s t over t. So we have t on the denominator, and we have e to the negative st. This is perfect. As you can see why in a bit. So, making that observation, let us rewrite this somewhere better. Making this observation, we can turn to the original function. So we know the Laplace transform of f of t is sorry. The Laplace transform f of t is integral e to the negative st f of t. What if we could make the e to the negative st an integral of this, a part of that? So let's go back to the e to the negative f of sorry, to the f of t over t. So the Laplace of f of t over t is equal to this. F of t, let's put it here, and then uh e to the negative st over t, let's put it here. All right, e to the negative st we know is this. All right, e to the negative st is equal to this. These two are equal to each other, so we can insert them together. So let's insert that integral in here. Infinity s e to the negative u t du dt. All right. Let's invite f of t here closer so we can get this. So it's a double integral as we discussed earlier. E to the negative ut f of t du dt. So what we can do after this? Let's try flipping the order, the dt and the du. So the region goes from s on the u-axis. Let's say the u-axis is this one and the t-axis is this one. So the s to infinity. So from s, so let's say this is s, all the way to infinity. And then on the t-axis is from 0 to infinity. So it's all of this. So let's, in flipping them, first, the dt goes from 0 to infinity anyway, so no problem there. And for the u-axis, it also goes from s to infinity, so no problems there, switching things up. And then e to the negative ut f of t dt du. This is the Laplace transform of f of t, but the u is the parameter instead of the s. So we can just put f of u in, big F of u, here, like that. This is the answer. The integral from s to infinity of f of u du. Don't say fu because that's rude. So how can we use this? Well, let's go to the bonus answer. Bonus. Bonus. The Laplace of sine t over t. What is that? Well, again, the Laplace of something t over t is just the integral 0 to infinity of f of u du. So what is the Laplace transform of sine? Laplace transform of sine is equal, sine bt is equals to b over s squared plus b squared. Let's put it somewhere. This doesn't fit. The Laplace of sine bt is equal to b over s squared plus b squared. So the Laplace of sine t b is equals to 1 here, so 1 over s squared plus b squared. But since we are having u here, sorry, not 0, s. Okay, since we have u here, we just insert u into s. Okay, this is 1. All right. So let us just substitute u for s, which is not that hard. 1 over u squared plus 1 du. This is the Laplace of sine t over t. So we just find the antiderivative of this. This is just 1 over 1 plus u squared, which is just, I don't know, arctangent of u. And then the bounds is from infinity to s. Arctan going to infinity, this goes to pi over 2. So pi over 2 minus arctangent of s. Why is this important? Because the Laplace of sine t over t is equal to this exact thing, which is the same as the previous question where we found the Dirichlet integral sine x over x. The process was we used e to the negative sx, right? But here it's negative e to the negative st because we're using the variable t. It's the same thing. And the same thing happens when s equals 0. The original integral is what we have left, st over sine t over t. So if s equals 0, then this is going to be pi over 2, which is sine t over t dt. And t is just the dummy variable, so it can be changed to x. So there we go. That's another way to prove the Dirichlet integral, or the integral earlier we found earlier. So surprising. That is 100 questions. That's it for now, but not really, because we have another question, brothers and sisters. Question 101, which is the final question. All right. The final question is the integral from 0 to pi over 2 of sine of n x dx. And the same thing, but cosine, where n is a natural number. All right. Let's get this out of the way. King's property states that this and that are the same. Why? Sine of pi over 2 minus x is equal to cosine of x, no matter how much the power is. And the power is just a natural number, so nothing hard there. So by King's property, this and that are the same. So yeah, we just proved that these and that are the same problem, so we can just ignore one of them. Let's just focus on the sign rule. There we go. So what we're going to do here? We're going to actually use the DI method, the integration by parts. And we're going to divide this into two parts. Let's make the D bigger. And that was wrong. So first one is sine of n minus 1 x. Sine to the n minus 1 x. The other one is going to be sine of x. When you multiply this is the original sine to the power n of x. So derivative of this is going to be n minus 1 times sine of n minus 2 x cosine x. And this is going to be negative cosine x. So what is the next step? Well, we just have an answer here. So we get negative sine to the n minus 1 x cosine x. And then the bounds we can set 0 to pi over 2. So we have to calculate for the bounds. And then we have to, the minus minus means addition. 0 to the pi over 2. Then n minus 1 is a constant, so let's bring it outside. Something like that. Then sine n minus 2. There's two cosines, so it's oops, sorry. X first. Then cosine squared x dx. Look here. Cosine of pi over 2 is 0. Sine of 0 is 0, no matter the power. So this is just a big fat 0. So all we really have to focus on is the second part. Let me just copy all of this. But remember, cosine squared x is 1 minus the sine squared x. So let's multiply that. And minus 2x dx. Then we can separate that actually. So, yeah, that's going to be what's happening here. And then sine of n minus 2x, then sine squared x. When you multiply them together, you just get n here because you just add the exponents. Let's remove this. And then let us define the original part. Let this be a function I of n. N is the power, and then I is just a function. So we're going to be focusing on the n here. And this is the result. So this is going to be I of n because it's the same integral. This is going to be I of n minus 2 since this is the same, but the power is just n minus 2. So that's the issue here. What we're going to do next is to make an equation out of this. So I sub n, I of n, sorry, equals to n minus 1 multiplied by I of n minus 2. Okay, that's an I, not a plus and minus. I. Minus n minus 1 I of n. Yeah. Move this to the other side, transpose. We get I of n. Then we multiply by 1 plus n minus 1. This is now equal to n minus 1 I n minus 2. Right? 1 plus n minus 1, this is going to be n. So we just divide n by both sides. We get I of n is equals to n minus 1 over n I of n minus 2. This is an important result, so let's move everything up. Sorry. All right. So this is the important result that we have. I of n is equals to n minus 1 over n I of n minus 2. This is a recursion. Why? There's an I of n, there's an I of n minus 2. Let's apply this one step deeper. Uh, from here, we can know that I of n minus 2 is equals to n minus 2 minus 1 over n minus 2. This is just replacing n minus 2 here. N minus 2 minus 2. We're replacing n with n minus 2. That's what we do in a function. This is equal to n minus 3 over n minus 2 I of n minus 4. So basically, this is recursion. N minus 4, we can apply that, and then so on and so on and so on. So we can get I of n equal n minus 1 over n multiplied by n minus 3 over n minus 2. Then I of n minus 4, right? And we can go one step further. N minus 5 over n minus 4, n minus 7 over n minus 6. Let's just with that. And then we multiply by I of n minus 2k. Again, k is a natural number. And yeah, we can go way further on the other side. So let's compress this together. This is going to be n minus 1 double factorial. So for those who do not know, remember that the factorial is just, so for example, we have 4 factorial is equal to 4 times 3 times 2 times 1, right? A 4 double factorial is equal to 4 times 2. We skip every other number. For example, 5 factorial is equal to 5 times 3 times 1. So we just skip every other number. So that's going to be what we're going to use here. Then n double factorial, and then I of n minus 2k. Now the question is, what is I of n minus 2k? Well, it could be one of two things. All right. So I of n minus 2k, uh, the first case would be if n minus 2k equals 1. This means that n is odd. All right. And originally is odd. So this will apply for when n is odd. So I of 1 or n minus 2k is equal to the integral from 0 to infinity, not infinity, pi over 2 sine x dx. This is negative cosine x, and then we get pi over 2 is 0 here. Cosine pi over 2 is 0 minus, and then cosine 0 is 1, so it's negative 1 here, positive 1. So uh, I of n minus 2k is 1 when n is odd. So the second case, this is case 1. Case 2, n minus 2k equals 0. This means n is even, right? Let's separate these together. Okay. So the integral from 0 to pi over 2 of 1, sine of 0, sine to the power 0 of x is just 1, dx. This is going to be x, and then pi over 2, 0. This is going to be pi over 2. So, summarizing everything, summarizing everything, I of n is equals to n minus 1 double factorial over n factorial, double factorial, multiplied by, let's assign a letter here. For here, we'll use the letter P, right? If n is odd, P is equals to 1. If n is even, P is equals to pi over, which are the uh, uh, conditions we laid earlier. So there you go. There is the special uh, restriction that n has to be greater than or equal to 2, but I think it can also apply to 1. So there we go. There has to be n in the first place. 0 factorial, I think, doesn't exist. I don't know, actually, it could be 1 if you think hard enough, right? But that's it. That is the formula. All right, let's rewrite this in terms of the integral again. Sine and x dx. This is also applicable to cosine, so because of the king property. So this is n minus 1 double factorial over n double factorial. P. Again, P is this two things. So why did I chose to do this for the final equation? Well, this is actually the Wallace integral formula. This will be useful in calculus 2 classes, so watch out for that. So that is how you make a formula for that. That is the 101st integral, and that is 100 integrals in total. Check the links in the description, or you'll find even cooler people who have done even better questionnaires and better videos than me. So yeah, there we go. Thanks for watching, and I'll see you in the next 100 integrals challenge that I do. This was hard and took a lot of days, so be sure to use it to study hard. Study hard. Bye.